For decades we thought we understood the deep sky. The Hubble Space Telescope gave us postcards from the edge of visibility, faint smudges sharpened into spirals and star-forming knots after long exposures and careful processing. Those pictures proved that galaxies are everywhere and that darkness is crowded with structure. Yet Hubble had limits. It saw mostly visible light with only a narrow reach into the near-infrared. Beyond that range, the first light from the earlier systems slid out of view, stretched by the expansion of space until it became invisible to Hubble's eyes. The James Webb Space Telescope was built to open those missing pages. Its primary mirror is a mosaic of gold hexagons more than 6.5 meters across a collecting area, far larger than Hubble's glass. A 5-layer sunshield the size of a tennis court keeps the observatory extremely cold, so that the faint heat of distant galaxies is not drowned by its own warmth. After launch, the telescope unfolded like precise origami and cruised to the second Lagrange point, a quiet gravitational perch about 1.5 million kilometers from Earth. From there, it stares outward with an unblinking eye, stable cold and tuned for ancient light. Infrared vision is the key. The universe expands, and expansion stretches light. What began as ultraviolet or visible light in the first galaxies arrives at our detectors as infrared. Dust also glows and absorbs in infrared, so an infrared telescope can both pierce dusty regions and measure the heat of the dust itself. Webb brings that vision to 3 principal instruments. The near-infrared camera maps distant fields with exquisite sharpness. The near-infrared spectrograph splits that light into spectra so we can read motion and chemistry. The mid-infrared instrument peers deeper into cool structures that Hubble could not penetrate. Together, these tools turn the sky from a photograph into a laboratory, where distance, temperature and composition can be read rather than guessed. From the first public release, the surprise was immediate. A patch of sky no larger than a grain of sand held at arm's length bloomed with thousands of galaxies. Some were stretched into elegant arcs by gravitational lensing, a natural magnifying effect in which mass bends the path of light. Others were tiny and red, their glow shifted so far that we were seeing them as they were when the universe was only a few 100 million years old. Astronomers expected clarity. They did not expect such abundance, such brightness, or such maturity so early. The basic intuition of how fast things grow at the beginning had to be tested again against reality. The result was not panic, it was curiosity sharpened into urgency. If the young universe looks busier than models predicted, some ingredient must be absent or mismeasured. Perhaps stars formed more efficiently inside dense gas than we thought. Perhaps early black holes grew quickly and poured energy into their neighborhoods, accelerating assembly. Perhaps dust and lensing have tricked our estimates, making small systems look older or heavier than they are. Webb did not overthrow cosmology in one stroke. It did something more valuable. It showed us where our pictures were too clean, and where the real sky is messier, richer and faster than our cartoon stories. This is why Webb matters. It is not simply a successor to Hubble. It is a different kind of witness. Because it sees in infrared, it can follow light that began its journey more than 13 billion years ago. Because it is cold and stable, it can pick out a whisper of water vapor in the atmosphere of a planet against the glare of its parent star. Because it both images and takes spectra, it can connect what we see to what things are made of and how they move. Each observation is not just a picture, it is a measurement that ties beauty to physics. The beginning is set, the mirror is cold, the instruments are awake. Now we turn to the first images that started the disturbance, and to the question that followed: how did galaxies become so big so soon? The first deep field of the James Webb Space Telescope arrived like a shockwave. It was meant as a demonstration image, a showcase for the power of the new observatory. Yet what it revealed went far beyond publicity. In a sliver of sky no larger than a grain of sand, Webb uncovered thousands of galaxies, some stretched and magnified by gravitational lensing, others so distant that their light had been travelling for over 13 billion years. Astronomers were prepared to see galaxies from early time, but they expected them to be small, irregular, clumpy primitive structures still learning how to organise stars. Instead, Webb showed objects that looked surprisingly mature. Some were large and disc-like, with hints of spiral arms. Others glowed with a brightness suggesting populations of stars already well established. The immediate question was blunt: how could galaxies grow up so fast? Models of cosmic history had predicted a slower beginning. After the Big Bang, it should have taken hundreds of millions of years for hydrogen gas to cool, condense and form the first stars. Only later would those stars gather into larger systems. But the galaxies Webb captured appeared far ahead of schedule. They were too big, too bright, too soon. The discrepancy became known as the too big, too soon problem. The puzzle deepened as follow-up observations poured in. Surveys such as JADES, the JWST Advanced Deep Extragalactic Survey, and SEERS, the Cosmic Evolution Early Release Science Program, found dozens more candidates at extreme redshifts. Some appeared less than 400 million years after the Big Bang, yet contained mass equivalent to billions of suns. To find such giants so early was like walking into a nursery and meeting fully grown adults among the infants. Were the models wrong? Or were the observations misleading? Astronomers considered possibilities. Perhaps the stellar populations inside these galaxies were unusually bright for their age, skewing estimates. Perhaps gravitational lensing made them look larger than they truly were. Perhaps the models of star formation efficiency at early times were incomplete. Each explanation softened the tension, but none erased it. What made the issue more striking was that Webb's instruments could measure spectra, not just images. The redshift values, the stretching of light that reveals distance and age, were confirmed for many of these galaxies. They truly were as far away and as early as they seemed. The conclusion was inescapable. Something in our understanding of the young universe was missing. This was not a small correction. If galaxies formed faster, then stars produced heavier elements sooner, and black holes might have grown quicker as well. The timeline of cosmic evolution would need to be revised. The neat division between the so-called Dark Ages, the epoch of Ryanization, and the emergence of structured galaxies was suddenly blurred. Webb had peeled back the curtain and revealed a universe busier, brighter, and older than expected. The emotional impact within the scientific community was a mixture of exhilaration and unease. For decades, cosmology had rested comfortably on the lambda cold dark matter model, a framework that predicted galaxy growth with impressive consistency. Now Webb was pushing at the edges of that comfort zone. It did not invalidate the model, but it forced astronomers to admit that the details of early star formation, black hole growth and feedback were less secure than once believed. This tension became the true gift of the first deep fields. Webb was not simply confirming expectations. It was raising new questions, forcing science to adapt and reminding us that the universe is not obliged to match our predictions. The cosmos is under no contract to be simple. It only shows us what it is, and we must adjust. And so the stage was set. The galaxies were larger, brighter and more complex than expected. But hidden among them were even stranger surprises, the first hints of supermassive black holes at an impossibly early age. That story would come next. As if the galaxies were not strange enough. Another discovery made the puzzle even deeper. Nestled within some of those bright early systems were signs of something far more extreme. Black holes of enormous mass already formed when the universe was still in its infancy. Supermassive black holes are usually found at the centers of galaxies today. They contain millions or even billions of solar masses, and they power quasars' cosmic beacons so bright they can outshine entire galaxies. Conventional wisdom had long assumed that these giants grew slowly, feeding on gas and merging with smaller black holes over billions of years. Yet Webb began to reveal quasars shining less than 1 billion years after the Big Bang. Some of them seemed to harbour black holes with masses measured in the hundreds of millions of suns. The timeline made little sense. To build such a monster, one would need seeds black holes born from the deaths of the very first stars. But those stars were thought to be massive, unstable and short-lived. Their remnants could weigh dozens or maybe hundreds of suns. Growing from that scale up to hundreds of millions in under 1 billion years strained every model of accretion and merger. The math did not fit. This contradiction gave rise to new ideas. Perhaps some black holes did not start small at all. Instead, clouds of primordial gas may have collapsed directly under gravity into objects weighing tens of thousands of suns right from birth. These direct collapse black holes would bypass the slow ladder of stellar death and instead begin as giants. Webb's detection of luminous quasars in early time gave momentum to this scenario. It suggested that the universe may have taken shortcuts, creating behemoths in the dark before galaxies themselves were fully settled. The data also pointed to a feedback loop. Supermassive black holes do not merely consume matter. They blast energy back into their surroundings, driving winds and jets that shape galaxy growth. In the early universe, such feedback could have accelerated the assembly of stars and heavy elements. Instead of galaxies forming first and then seeding black holes, perhaps the reverse was also true. Black holes helped galaxies come together. It was a role reversal, and it upended long-held assumptions. Yet as powerful as these new theories sound, none resolve the tension completely. Accretion even at the most extreme rates takes time. Direct collapse requires very specific conditions, and the number of early quasars seen by Webb suggests that such conditions were not rare. The cosmos was producing giants efficiently, and we still do not fully understand how. This mystery is more than a curiosity. Supermassive black holes anchor the evolution of galaxies, determine the growth of clusters, and may even influence the large-scale structure of the universe. If they appeared too soon, then our models of cosmic history are missing something crucial. Webb has not only forced us to redraw the early timeline of galaxies, it has also forced us to rethink the engines that drive them. The first deep fields showed galaxies too big too soon. The early quasar discoveries showed black holes too heavy too early. Together they painted a universe that matured with breathtaking speed, a cosmos that wasted no time in building complexity. And as Webb kept looking, it found yet another layer of surprise. Galaxies that lived fast and died young, shutting down star formation far earlier than anyone expected. While some galaxies in Webb's deep fields appeared shockingly mature, others revealed a different kind of mystery. They seemed to have already stopped making stars, even though the universe itself was barely a billion years old. These objects became known as quiescent galaxies, or more poetically Sleeping Beauty galaxies. Star formation is the heartbeat of a galaxy. Gas clouds collapse, ignite, and light up the sky with newborn stars. In the early universe, when matter was dense and gas was abundant, astronomers expected galaxies to be in overdrive, forming stars at furious rates. And indeed, many were. But Webb identified galaxies that appeared silent, their gas depleted, or shut off their stellar populations, aged and fading. It was as though these galaxies had sprinted through youth, burned their fuel too quickly, and then fallen into an early slumber. The implications are startling. For a galaxy to go dormant so early, something dramatic must have intervened. One explanation points to feedback from central black holes. As massive black holes consume gas, they release jets and winds that can blow away surrounding material, cutting off the fuel for new stars. Another possibility is environmental. Perhaps these galaxies formed in dense regions of space where gas was stripped by interactions with neighbours, or heated beyond the point where it could collapse again. Still another theory suggests that early starbursts may have simply used up the gas supply, leaving nothing behind. Whatever the cause, the result is the same. A galaxy that should be vibrant and chaotic is instead calm and fading long before its time. This challenges our picture of cosmic history. The narrative of gradual growth of galaxies steadily building stars for billions of years must make room for exceptions. Some galaxies lived fast and died young. Webb's ability to dissect the light from these galaxies provided further evidence. Spectra showed the chemical fingerprints of older stellar populations, heavy elements already abundant, but little sign of fresh gas. Their colours were red not only from distance, but also from age, indicating stars that had already evolved off the main sequence. These were not primitive clouds, just beginning to shine. They were veterans already past their prime. The existence of Sleeping Beauty galaxies raises difficult questions. How common are they? If they represent only a small fraction, they may be unusual curiosities. But if Webb finds many more, they could reshape our understanding of galaxy life cycles. The possibility emerges that the universe has multiple pathways, some galaxies roaring ahead in prolonged bursts of creation, others racing through their fuel and collapsing into quiet embers. These galaxies also have consequences for cosmic reionization, the era when ultraviolet light from young stars ionized the fog of hydrogen that filled the universe. If many galaxies shut down too early, then who provided the photons that ionized the cosmos? Did other more active systems compensate? Or does the quiescent population hint at a hidden balance between life and death on a galactic scale? For now, Sleeping Beauty galaxies remain a riddle. They remind us that the early universe was not uniform but diverse, filled with actors that played their roles at wildly different tempos. Some galaxies blazed like fireworks, others dimmed into silence, and Webb's task and ours is to weave these contrasting stories into a coherent history. But the surprises did not end there, Because while Webb revealed galaxies that fell asleep too soon, it also showed us galaxies that were astonishingly efficient, punching far above their weight. Tiny green specks that turned out to be powerhouses of star formation. Among the oddities revealed by Webb's deep fields were tiny compact galaxies that glowed with an unusual light. Astronomers had seen hints of them before in ground-based surveys where they earned the nickname green peas because of their small size and distinctive colour. Now with Webb's infrared eyes, their true nature came into focus, and the picture was even stranger than expected. Green pea galaxies are small, often no more than a few thousand light years across, yet they shine with intense emission from ionized gas. They are star factories forming new suns at a rate that rivals or even exceeds much larger galaxies. Their spectra are dominated by strong lines of oxygen and hydrogen, giving them their characteristic glow. In the early universe, these galaxies were far more common, and Webb suggests they played an outsized role in shaping cosmic history. Why are they important? Because galaxies like these may have been crucial in reionizing the universe. During the first few 100 million years after the Big Bang, the cosmos was filled with neutral hydrogen gas that blocked ultraviolet light. At some point, that gas became ionized, allowing light to travel freely. The photons needed to drive this transition had to come from somewhere. Green pea galaxies, with their intense bursts of young hot stars, may have supplied a large fraction of that radiation. In other words, these tiny specks could have lit up the universe, ending the cosmic dark ages. But green peas are not the only peculiar shapes in Webb's view. Gravitational lensing. The bending of light by massive clusters of galaxies has created illusions that reveal both the power of gravity and the depth of space. One striking case is the so-called infinity galaxy, where a single background system appears stretched into a mirrored curve resembling a cosmic sideways figure 8. These distorted arcs are more than curiosities. They are natural telescopes magnifying galaxies too faint to be seen otherwise. Webb uses these chance alignments to study structures that would normally be beyond its reach. Another surprise came in the form of supernova observed multiple times. When a massive star explodes behind a gravitational lens, the light can travel along different paths around the lensing mass. Some paths are longer than others, so the same explosion arrives at different times. In effect, we watch the same star die more than once, separated by days, months, or even years. Webb has captured such echoes, turning supernovae into cosmic time machines. These events are not only visually stunning, but also invaluable for cosmology, offering a way to measure distances and test models of dark matter distribution in lensing clusters. The diversity of galaxies and phenomena in these deep fields drives home a point. The early universe was not simple. It was crowded with actors performing very different roles. Some galaxies matured far too quickly. Some shut down before their time. Others, like the green peas, burned furiously, flooding space with ionizing light. And behind them all, gravity sculpted the stage, bending and distorting the view, reminding us that space itself is not passive, but an active participant in the cosmic drama. With every observation, Webb forces astronomers to ask new questions. If small galaxies could have such enormous impact, how much of the cosmic history have we underestimated by focusing only on giants? If gravitational lensing reveals hidden worlds, how many more lie just beyond our direct sight? And if supernova echoes can repeat across time, what else might the bending of light reveal about the architecture of space-time? The stage was set with mature galaxies and early quasars. Then came the sleeping beauties and the green peas. Each discovery complicates the picture, showing that there is no single template for how galaxies live and die. And as Webb shifted its gaze from galaxies to worlds, the surprises only multiplied because it began to read the atmospheres of planets orbiting other stars. If Webb's deep fields overturned our understanding of galaxies, its studies of exoplanets opened an entirely new frontier. For the first time, humanity had an instrument capable not only of detecting planets around other stars, but of analysing their atmospheres in detail. Where Hubble hinted and guessed, Webb measures and reveals. Suddenly alien worlds are no longer points of light. They are places with weather chemistry and perhaps even conditions that whisper of life. The technique is deceptively simple in concept. When a planet passes in front of its star, a fraction of the starlight filters through the planet's atmosphere before reaching us. Molecules in that atmosphere absorb specific wavelengths, leaving faint fingerprints in the spectrum. Webb, with its infrared sensitivity and extraordinary stability, can detect those fingerprints with precision. In practice, it means that when a planet transits, Webb can read its skies as if holding a prism to a distant world. The first demonstration came quickly. WASP 96b, a hot gas giant orbiting close to its star, revealed the clear signature of water vapour. The spectrum was so sharp and unambiguous that it stunned even seasoned astronomers. Hubble had hinted at water in exoplanets before, but Webb made it undeniable. Here was proof that the method worked exactly as promised. The door to comparative exoplanetology swung open. Soon after, Webb turned its gaze to stranger targets. On planets like WASP 39b, it detected not only water, but also carbon dioxide and sulfur dioxide, a chemical cocktail shaped by photochemistry under the blaze of a parent star. In the atmosphere of K2-18b, a sub-Neptune world orbiting in the habitable zone of a red dwarf star, Webb spotted methane and carbon dioxide, and tantalizing hints of a compound called dimethyl sulfide. On Earth, that molecule is produced almost exclusively by marine plankton. The detection is tentative, debated, and far from confirmation of life. Yet the very fact that Webb can sniff such delicate signals across light years is astonishing. Even exotic giants turned out to hold surprises. Observations of a famous hot Jupiter called HD 209458b, discovered in 2001, revealed clouds rich in silicate particles. In other words, the benchmark hot Jupiter may experience literal rain of glass driven sideways by winds racing thousands of kilometers per hour. These are not friendly environments, but they demonstrate the sheer diversity of planetary weather that Webb can now document. Beyond individual worlds, Webb has begun to map trends. It is comparing hot Jupiters, warm Neptunes, super-Earths, and everything in between. The results suggest that planetary atmospheres are as varied as snowflakes influenced by star-type orbital distance, mass, and history. Some retain thick blankets of hydrogen and helium. Others lose their gases to stellar winds and radiation, leaving bare rocky cores. The range of outcomes is vast, and Webb is only beginning to chart it. The implications are profound. For the first time, we are not only cataloguing planets, but characterizing them. We are learning what alien skies contain, how alien climates behave, and where the line between sterile rock and potential habitability may lie. Webb has transformed the search for life from speculation into experiment. Each new spectrum is a data point in the greatest survey humanity has ever attempted, the search for company in the cosmos. And yet, as remarkable as these exoplanet results are, they represent only one part of Webb's mission. Because while it peers across light years to analyse distant atmospheres, it has also turned back to our own cosmic neighbourhood. Even the familiar planets of our solar system look utterly new under its gaze. Though designed to study the distant universe, Webb has also turned its golden mirror inward toward our own solar system. The results have been just as striking, transforming the familiar into the extraordinary. By observing in infrared, Webb can reveal details that no other telescope has captured, peeling back layers of atmosphere rings and icy surfaces. Take Neptune, for example. To the naked eye through Hubble, Neptune appeared as a soft blue disk, its methane absorption giving it a distinct colour. Webb's view, however, stripped away the glare of reflected sunlight and exposed the planet's delicate ring system in astonishing clarity. Faint arcs and incomplete rings, once glimpsed only by the Voyager spacecraft, now glowed clearly in infrared. Around the planet, Webb caught small moons shining like points of light, each with its own signature in the infrared spectrum. For the first time in decades, Neptune revealed its full architecture, a reminder that even in our backyard, mysteries remain. Uranus was no less dramatic. Hubble showed it as a bland cyan orb tilted almost onto its side. Webb's images, by contrast, revealed its brilliant polar cap, a seasonal feature linked to its extreme tilt and long orbit. Faint concentric rings appeared, some so delicate they had never been seen with such clarity from Earth. In the infrared glow, Uranus transformed from a dull world into a dynamic system, its atmosphere alive with storms, and its surroundings crowded with rings and moons. Webb also set its sights on smaller, stranger bodies. When the icy centaur Chariklo passed in front of a distant star, Webb recorded the occultation. The star's light dimmed and reappeared twice, a signature of Chariklo's thin ring system. Detecting such subtle events requires extreme precision. Yet Webb accomplished it, proving that its stability can reveal the most delicate features of small, distant worlds. The icy moons of Jupiter and Saturn also drew attention. Europa, with its cracked surface and potential subsurface ocean, showed hints of complex chemistry in its thin atmosphere. Webb detected carbon dioxide on Europa's surface concentrated in specific regions, a clue that the material may have come from the ocean below. On Enceladus, Saturn's tiny moon, famous for its geysers, Webb captured a vast plume of water vapour stretching thousands of kilometres into space, larger than any plume seen before. Such findings fuel speculation that these hidden oceans may harbour the ingredients for life. Closer to the edge of the solar system, Webb observed comets and trans-Neptunian objects. It detected the gases released as comets warmed near the Sun, reading their molecular composition with exquisite sensitivity. For Kuiper Belt objects far beyond Neptune, Webb measured colours and infrared spectra, probing their surfaces for signs of ices, organics and geological history. Even Pluto and Eris, once faint and distant, now offer clearer chemical fingerprints. These observations highlight a simple truth. Webb is not limited by distance alone. Whether aimed at a quasar billions of light years away or a moon within our own solar system, its instruments deliver transformative insights. It can study the chemistry of atmospheres, the structure of rings and the plumes of icy worlds with the same precision it brings to galaxies. By turning its gaze homeward, Webb reminds us that exploration is not only about the distant and the ancient. The frontier also exists close at hand in the planets and moons we thought we knew, but which still hold secrets waiting to be revealed. And as it moves from our solar system back into the wider cosmos, Webb confronts perhaps its greatest challenge yet, reconciling its discoveries with the established model of the universe itself. The lambda-cold dark matter model has been the foundation of the modern cosmology for decades. It describes a universe dominated by dark energy, symbolized by the Greek letter lambda, and cold dark matter, invisible particles that shape the skeleton of cosmic structure. Within this framework, galaxies form slowly along filaments, stars light up gradually, and supermassive black holes grow steadily over billions of years. For a long time, the data matched the model remarkably well, but then James Webb arrived. From its earliest observations, Webb revealed galaxies that were too massive, too organised and too bright at times when the universe should have still been struggling to assemble its first building blocks. It showed supermassive black holes already in place before theory said they had time to form. It found quiescent galaxies that had already shut down star formation while the cosmos was still young. Each of these discoveries taken alone might have been explained as an outlier. Together they hinted at cracks in the framework. The problem is not that lambda-cold dark matter is wrong in principle. It still describes the overall geometry of the cosmos, the distribution of galaxies on the larger scales, and the history of expansion with remarkable accuracy. The tension lies in the details, in the speed of early growth. If galaxies reached maturity so quickly, either star formation was far more efficient in the early universe, or something else was at work, a missing ingredient in the recipe. Some scientists suggest that dark matter itself may not behave as simply as the cold assumption implies. Perhaps it interacts weakly with ordinary matter in ways we have not measured, or perhaps it clumps differently at small scales. Others argue that feedback from early black holes, exploding stars, and violent outflows may have turbocharged galaxy growth. Still others explore more radical options: variations in dark energy, changes in fundamental constants, or even new physics at high energies. Webb does not provide final answers to these questions, but it provides the evidence that forces them to be asked. Every deep field it captures becomes a testing ground where theorists run simulations and compare them to what Webb actually sees. In many cases, the simulations underproduce galaxies of the size and brightness that Webb finds. Adjusting parameters helps, but the degree of tuning required is uncomfortable. The tension is not fatal, but it is undeniable. This is the essence of scientific progress. Models are tested against reality, and when reality refuses to conform, the models must evolve. Webb has not destroyed the standard model of cosmology, but it has shaken it, reminding us that even the most successful frameworks are provisional. The early universe is proving more dynamic, more complex, and more chaotic than expected, and the story is still unfolding. For every paper that highlights tension, another suggests possible reconciliation. The debate is alive, and Webb has become the referee. As more data arrives, the picture will sharpen. Perhaps the model will adapt. Perhaps a new paradigm will rise. Either way, the universe has issued a challenge and cosmology must respond. What makes this moment thrilling is that we are witnessing it in real time. Decades from now, scientists may look back on Webb's early years as the turning point, the era, when familiar models began to bend under the weight of new evidence. For now, we live in the uncertainty, and uncertainty is where discovery thrives. And even as theory struggles, Webb's eye continues to wander. It finds not only galaxies and quasars, but phenomena stranger still, worlds and systems that seem to whisper of physics we have not yet grasped. The deeper Webb looks, the more it reveals puzzles that cannot yet be explained. Some galaxies, instead of showing the chaos expected from early times, appear astonishingly calm. Their stars orbit in neat disks, their shapes organized as if billions of years of evolution had already passed. How can order arise so quickly in a universe that should still have been turbulent? Computer simulations struggle to reproduce such serenity. They predict clumps mergers and violent interactions. Yet Webb shows us graceful spirals when there should have been only fragments. Other galaxies defy expectations in a different way. They shine with unusual colors or line emissions that do not match standard models of stellar populations. In some cases, the spectra hint at exotic chemical compositions, suggesting that heavy elements formed more rapidly than thought. In others, the brightness cannot be accounted for without invoking star formation rates far beyond what our physics would normally allow. Are we misinterpreting the data, or is the universe telling us it had shortcuts we have yet to understand? Then there are the transient events, sudden flashes, flickers or signals that appear briefly in Webb's detectors. Some may be supernovae, the explosions of massive stars. Others may be outbursts from active black holes, but a few remain unexplained. Because Webb is so sensitive, it sometimes picks up faint sources that no other instrument can confirm. They may be real, or they may be artifacts of observation. Until follow-up studies are made, they linger as tantalizing maybes, mysteries waiting for resolution. Even the dark gaps in Webb's images carry weight. The expectation was that galaxies should fill the sky almost uniformly at these depths. Yet there are patches where galaxies seem scarcer than predicted. Are these voids real, signaling large-scale variations in structure, or are they quirks of observation? Mapping them precisely could teach us about the distribution of dark matter and the earliest seeds of cosmic architecture. And in the spectra of some high-redshift galaxies, astronomers have found patterns that do not fit the templates. Emission lines appear shifted, broadened, or missing altogether. In some cases, the data suggest massive outflows of gas, as though galaxies were ejecting material with ferocity not accounted for in simulations. In others, the chemical ratios imply enrichment far earlier than expected, as if the universe's first stars lived and died in a compressed frenzy, scattering heavy elements in record time. Each of these mysteries by itself might be a footnote. Together, they form a chorus of questions that remind us how young Webb's mission still is. We are at the beginning of decades of discovery. Every strange signal is a lead, every contradiction a potential breakthrough. This is how science advances, not with perfect answers, but with better questions. Webb has given us galaxies that grew too fast, black holes that appeared too early, stars that stopped forming too soon, and worlds with skies that defy imagination. And now it hints at phenomena that we cannot yet categorize. Are we seeing physics beyond our current models? Or are we simply glimpsing corners of the universe where chance and chaos combine to create exceptions? The only certainty is that more surprises are waiting. The next frontier will not just be about galaxies or planets, but about life itself. Because Webb's ability to read atmospheres has already delivered the first controversial hints of molecules that on Earth are tied to biology. Whether those signals prove real or not, they mark the dawn of a new chapter, the search for signs of life across the stars. Among all the discoveries Webb has delivered, none stir the imagination more than its glimpses into alien skies. For the first time, we can ask not only what exoplanets are made of, but whether they show signs that could hint at life. The answers are tentative, controversial and fragile, yet even the possibility sends ripples through science and society alike. The case of K2-18b stands out. This world orbits a red dwarf star about 120 light-years away. It is larger than Earth but smaller than Neptune, a sub-Neptune that does not exist in our solar system. Its position in the habitable zone, where temperatures might allow liquid water, made it a prime target for Webb's instruments. When the spectra came back, they contained not just water vapour and carbon dioxide, but possible traces of a molecule called dimethyl sulfide. On Earth, this compound is almost entirely produced by marine plankton. The claim was cautious. The signal was faint and astronomers warned of uncertainties. Noise and instrumental effects could mimic the signature. More observations are needed. Yet the mere suggestion that Webb could detect such a molecule at such a distance was breathtaking. It showed that the search for biosignatures, chemical hints of life, had moved from dream to reality. Other worlds have added to the intrigue. On WASP 39b, a hot giant scorched by its star Webb detected sulfur dioxide in the atmosphere. This is not a biosignature, but it proved that Webb can observe photochemistry in action, reading how starlight transforms alien skies. On planets where conditions are gentler, similar methods could reveal gases like methane oxygen, or combinations that cannot be explained by geology alone. The challenge is interpretation. Life leaves chemical fingerprints, but so do volcanism, lightning, and other natural processes. To claim detection of life, astronomers will need multiple lines of evidence. The presence of gases in disequilibrium repeated in multiple transits consistent across instruments. Webb's results are the first steps along this path. They are not proof, but they are proof of ability. This ability is what matters most. We now know that it's possible to examine a planet dozens or hundreds of light years away, and ask whether its chemistry resembles that of a living world. That question, once confined to philosophy or fiction, has entered the domain of measurement. Each new spectrum expands the list of candidates. Each transit adds a piece to the puzzle. For now, the signals remain whispers in the noise, but as Webb continues to observe and as future missions join it, the whispers may grow louder. Whether or not K2, 18b, or any current target proves to harbour life, the principle has been established. The universe is within range, and the tools to ask the biggest question of all, are we alone?, are finally in our hands, and while exoplanets ignite the imagination, Webb's reach extends even further. It does not only search for life, it also reveals the fate of stars, the explosions that seed the cosmos with heavy elements, and the cycles of birth and death that shape everything we see. Every planet, every ocean, every living cell depends on elements forged in stars. Hydrogen and helium were born in the Big Bang, but everything heavier, carbon, oxygen, iron and beyond, was created in stellar furnaces and scattered by violent deaths. To understand how the universe became habitable, we must understand how stars lived and died in the earliest epochs. This is where Webb's vision is proving revolutionary. When Webb turns its gaze towards stellar nurseries, it pierces the curtains of dust that hide them from visible light. Vast clouds that looked opaque in Hubble's images now glow in filigree detail. We see stars forming inside cocoons, jets streaming out and knots of gas collapsing under gravity. Webb's instruments record the chemistry within these clouds, measuring water, carbon monoxide, and complex organics, even as new suns ignite. These are not abstract numbers, they are the raw ingredients for future planets, comets, and perhaps life itself. But the story does not end with birth. Stars die and their deaths enrich the cosmos. Webb has already observed supernovae in distant galaxies, some magnified by gravitational lensing, so that we see them multiple times at different stages. The spectra reveal shockwaves colliding with surrounding gas, creating new elements in the process. Webb's sensitivity allows astronomers to track how those elements are dispersed into the interstellar medium, seeding the next generation of stars. In one striking case, Webb captured the aftermath of a supernova, where carbon and oxygen were seen streaming into space. These are the atoms that form the backbone of biology. Without them, planets would be barren and life as we know it could not exist. Webb's observations confirm that even in the earliest billion years, stars were already enriching the universe with the building blocks of life. Webb has also turned its eye to dying stars closer to home. The Southern Ring Nebula, a planetary nebula formed by a star shedding its outer layers, became one of Webb's first iconic images. In infrared, delicate shells of gas glow with haunting beauty. Inside, a white dwarf star remains the smouldering core left behind. Webb's instruments revealed complex molecules in the nebula, showing that even the quiet deaths of stars contribute to cosmic chemistry. By studying both stellar birth and stellar death, Webb provides a complete view of the cosmic cycle. Gas clouds collapse, ignite, shine, and eventually explode or fade, returning enriched material to space. Over countless generations, this recycling transforms a simple universe into a complex one capable of supporting planets and biology. These insights connect directly to the questions of habitability. If heavy elements were produced and dispersed earlier than expected, then rocky planets may have formed earlier too. Life in principle could have had more time to emerge than models once allowed. Webb is not only rewriting the timeline of galaxies, but also the timeline of potential life in the cosmos. And as if that were not enough, Webb has shown us phenomena that push even further. Not just the birth and death of stars, but the dramatic collisions that reshape galaxies themselves. Galaxies are not isolated islands. They interact, collide, and merge, reshaping one another in cosmic dances that span hundreds of millions of years. With its infrared vision, Webb has begun to capture these encounters in unprecedented detail, revealing the raw mechanics of how the largest structures in the universe grow. One of the most striking early images from Webb showed Stephan's quintet, a compact group of 5 galaxies locked in gravitational interplay. To visible light, the scene looked like a tangle of faint smudges, but in Webb's infrared, bridges of gas stretched between galaxies, shockwaves flared where systems collided, and individual clusters of newborn stars glowed like embers scattered across the scene. Webb did not just show that galaxies collide, it showed the anatomy of collision itself, the transfer of energy, the ignition of starbursts, and the stirring of gas that will one day form new worlds. Such interactions are not rare, in fact they are essential. Our own Milky Way has cannibalized smaller galaxies throughout its history, and in a few billion years it will merge with the Andromeda Galaxy in a colossal union. Webb's observations of current mergers offer a preview of that future. We see disks ripped apart, tails of stars flung outward for hundreds of thousands of light years, and central black holes feeding furiously as gas is funneled into their grasp. These events are violent, but they are also creative. Collisions trigger waves of star formation, seeding the universe with fresh generations of suns. Webb's spectra allow astronomers to go beyond the images. By analysing the motion of gas in colliding galaxies, scientists can map the flows of material, measure the turbulence, and determine how efficiently new stars are born. The data reveal regions where gas is compressed to extremes, creating stellar nurseries far more intense than in calmer galaxies. In some systems, thousands of stars ignite almost simultaneously, producing superstar clusters that may survive for billions of years. The impact of mergers extends to central black holes. When galaxies collide, their central giants are drawn together, eventually merging in titanic events that release gravitational waves strong enough to ripple space-time itself. Webb cannot detect those waves directly, but it can witness the feeding frenzy as gas falls inward. By catching quasars in merging galaxies, Webb provides vital clues to how supermassive black holes grow in step with their hosts. Even more subtle are the signs of past mergers, shells, ripples, and faint tidal streams surrounding seemingly calm galaxies. Webb's sensitivity allows astronomers to trace these faint relics, the scars of ancient encounters that shaped galaxies long ago. Every ripple is a fossil telling a story of cosmic cannibalism written in stars. What emerges from these observations is a portrait of the universe as a place of constant motion and transformation. Galaxies are not static. They are evolving communities torn apart and reassembled by gravity's relentless hand. The quiet spirals and ellipticals we see today are the survivors of countless violent unions. Without mergers, galaxies would be smaller black holes, weaker, and the universe less diverse. By showing us these collisions in progress, Webb reminds us that creation and destruction are inseparable. Out of chaos comes order, and from the wreckage of shattered systems, new structures arise. And while galaxies clash on grand scales, Webb also captures the delicate details of the smaller engines that shape them, the clouds of gas and dust where stars themselves are born. If galactic mergers are the violent symphonies of the universe, then star-forming nebulae are its delicate sculptures. They are the nurseries where gravity dust and radiation carve structures of breathtaking beauty. Hubble once made such regions iconic, capturing towering columns of gas in the Eagle Nebula and glowing walls of Orion. Yet Webb's infrared vision has revealed layers of detail never seen before, exposing the hidden choreography of stellar birth. One of Webb's most celebrated images is the Carina Nebula, a vast complex of gas and dust about 7,500 light-years away. To visible light, Carina is a landscape of dark clouds silhouetted against starlight. Webb turned that darkness transparent. Behind the walls of dust, thousands of newborn stars emerged, each one carving cavities with its radiation and winds. The scene looked like a mountain range at sunset, jagged peaks glowing with heat, but every peak was a cloud collapsing under gravity on the way to becoming a star. In Orion, Webb revealed the protoplanetary disks, small dense structures around young stars where planets are forming. Hubble had shown hints of these disks silhouetted against glowing gas. Webb's infrared cut through the glare and captured their inner regions where dust grains are colliding and sticking together. These disks are the seeds of solar systems, and Webb can measure their chemistry, tracking water vapor and organics that may someday be delivered to planets. Beyond our neighborhood, Webb has turned its gaze to starburst galaxy systems where star formation is occurring at extreme rates. In galaxies like NGC 346, Webb traced filaments of dust threaded with hundreds of infant stars, some no more than a few million years old. The instruments detected icy molecules and carbon compounds clinging to dust grains, evidence that the building blocks of life are present even in the chaos of stellar birth. What makes Webb unique is not only the clarity of its images, but the precision of its spectra. Astronomers can now measure the temperature, density, and composition of star-forming clouds with unprecedented accuracy. They can distinguish between regions heated by massive stars and cooler zones where smaller suns are forming. They can watch jets blasting out of protostars, carving holes in their birth clouds. The data transform nebulae from works of art into laboratories, and the implications ripple outward. If Webb shows that stars and planets form faster than expected, then the timeline for habitability shifts once again. Complex chemistry may begin earlier, planets may assemble sooner. Life, at least in principle, may have had more opportunities to take root across the cosmos. These nebulae remind us that creation is messy. Stars are not born in isolation but in clusters, their light and winds shaping one another's growth. Some emerge massive and short-lived, destined to explode. Others are small and stable, capable of shining for tens of billions of years. Webb's images capture this interplay, the crowded, competitive nurseries where the future of galaxies is decided. And while Webb shows us the origins of stars, it also peers into the shadows cast by something far more enigmatic, the invisible matter that makes up most of the universe. Because behind the beauty of nebulae and the chaos of mergers lies a deeper puzzle, the nature of dark matter and how Webb may help us glimpse its fingerprints. Behind every luminous star and glowing nebula lies a framework we cannot see. Dark matter, invisible, non-luminous, yet overwhelmingly influential, shapes the skeleton of the cosmos. It makes up far more of the universe than ordinary matter, yet it has never been detected directly. Instead, its presence is inferred through gravity, the way galaxies spin, the way clusters bind, the way light bends. And Webb, with its exquisite sensitivity, has begun to trace dark matter's fingerprints with clarity never achieved before. One of Webb's greatest advantages is its ability to exploit gravitational lensing. When a massive cluster of galaxies sits between us and a more distant target, the cluster's gravity bends and magnifies the background, light creating arcs, rings, and multiple images. These distortions are not only beautiful, they are maps. By measuring them precisely, astronomers can reconstruct the distribution of mass within the lensing cluster. That includes not just stars and gas, but the unseen dark matter that provides most of the weight. In the first, Webb deep fields arcs of lensed galaxies appeared in abundance. Some were stretched into elegant curves, others split into multiple copies. The detail was so fine that astronomers could measure tiny differences in brightness and shape clues to how dark matter is clumped on small scales. These measurements are critical because they test whether dark matter is truly cold, moving slowly and clumping strongly, or whether it might behave differently, spreading out more smoothly than expected. Webb's data also sharpen tests of alternative ideas. Some scientists argue that perhaps dark matter does not exist at all, and that gravity itself changes on cosmic scales. These theories, known as modified gravity models, predict lensing patterns that deviate from those produced by cold, dark matter. With Webb's precision, astronomers can check the subtle details. The thickness of arcs, the relative timing of supernova echoes the structure of faint galaxy halos to see which theory survives. So far, the evidence continues to support dark matter, but the story is far from over. Webb has revealed small discrepancies, places where the lensing patterns hint at substructures not accounted for by visible matter. These could be clumps of dark matter, invisible mini-halos that theory predicted but had been hard to detect. If confirmed, they would be a triumph for the cold dark matter paradigm, showing its fingerprints directly. Beyond clusters, Webb's view of distant galaxies also informs dark matter studies. By measuring rotation curves and mass distributions at earlier epochs, astronomers can see how galaxies assembled within their dark halos. The surprising maturity of some early galaxies raises questions here too. Did dark matter halos form faster than expected? Did their gravity accelerate the growth of stars and black holes? Webb is helping to constrain these possibilities, connecting luminous structures to the invisible scaffolding beneath. Dark matter remains one of the greatest mysteries of physics. It does not shine, it does not absorb, it does not interact in ways we can detect except through gravity. And yet it outweighs the matter of stars, planets, and people by more than 5 to 1. Webb cannot solve the riddle alone, but it provides the clearest window yet into how dark matter shapes the cosmos. Each arc of light, each distorted galaxy is a clue. Together they may lead us closer to understanding what most of the universe is really made of. And as Webb probes the invisible skeleton, it also illuminates the role of dark energy, the even more mysterious force driving cosmic acceleration. That story stretches the imagination even further, and Webb is only beginning to hint at its reach. If dark matter provides the hidden skeleton of the universe, then dark energy is the unseen breath that pushes the skeleton apart. It is stranger still, an unknown force discovered not by direct detection, but by the way galaxies flee from each other faster and faster. In the late 1990s, astronomers using supernovae as cosmic mile markers realized that the expansion of the universe is accelerating. Instead of slowing under gravity as everyone had expected, space itself is stretching more quickly with time. To account for this, cosmologists invoked dark energy, an invisible pressure filling all of space. For decades, the evidence for dark energy has come from surveys of galaxies, measurements of the cosmic microwave background, and maps of large-scale structure. But these are broad strokes, averages over billions of light years. Webb provides something new, a close detailed view of galaxies and supernovae at extreme distances, allowing astronomers to test whether dark energy behaves the same way everywhere and at every time. Webb's infrared sensitivity makes it ideal for observing Type Ia supernovae, the standard candles used to measure cosmic distances. These explosions, visible across billions of light years, allow astronomers to plot how fast the universe was expanding when the light was emitted. By extending the supernova record deeper into the past, Webb refines the curve of cosmic acceleration. If the expansion rate bends differently than expected, it could signal that dark energy evolves with time rather than being a simple constant. Already hints of tension are emerging. Webb's precise measurements of galaxy brightness and distances sharpen a long-standing conflict known as the Hubble tension. Local measurements of expansion based on nearby galaxies and supernovae give a higher value than predictions derived from the early universe. The discrepancy remains unresolved, and Webb's data may either bridge the gap or deepen the divide. If the latter, then something fundamental is missing from our cosmological picture. Another way Webb contributes is through gravitational lensing. The arcs and distortions caused by massive clusters depend not only on dark matter, but also on the geometry of space itself. By analysing many lensing systems at different redshifts, astronomers can test how cosmic expansion has changed. This in turn constrains models of dark energy, whether it is a cosmological constant, a dynamic field, or something stranger still. Dark energy remains the most mysterious component of the cosmos. It accounts for nearly 70% of the universe, yet we do not know what it is. It could be a property of space itself, a new kind of energy field, or a sign that our understanding of gravity breaks down at the largest scales. Webb cannot solve the mystery alone, but it sharpens the tools. It pushes observations to earlier times when the first galaxies were forming, and it allows us to see whether the fingerprints of acceleration are consistent across epochs. What Webb teaches above all is humility. The universe is not obliged to follow our simplest ideas. Dark energy is not an elegant addition to the equations. It is a confession that we do not yet understand why space expands as it does. With Webb's help, we are beginning to test the edges of that ignorance. And as Webb contributes to these vast questions of matter and energy, it also continues to dazzle with the unexpected images and signals that define neat categories, pushing astronomy into realms that feel almost surreal. Not every surprise from Webb fits neatly into categories of galaxies, stars, or planets. Some discoveries are stranger, almost surreal glimpses that make the universe feel less like a predictable machine and more like a realm of cosmic artistry. One of these is the so-called cosmic infinity system. Through the lensing power of a massive galaxy cluster, Webb captured a distant galaxy stretched and mirrored into a sideways figure 8. To the human eye, the shape looks like a symbol drawn deliberately, yet it is the result of gravity bending space-time itself. The arcs are more than visual curiosities, they provide magnification, turning a faint and unreachable galaxy into an object we can study in detail. Webb reads the stretched light and turns a cosmic trick into data, but the image remains haunting a reminder that space can sculpt illusions stranger than imagination. Another wonder lies in time itself. Webb has observed supernovae exploding behind gravitational lenses, and because the light takes multiple paths around the lensing mass, the same event appears more than once. Imagine seeing a massive star detonate then months later, watching it explode again and again, each flash arriving by a different route. These time-delayed supernovae are not only mesmerizing, they are powerful tools. By measuring the delay precisely, astronomers can test the expansion of the universe and probe the distribution of dark matter in the lensing cluster. Yet to the public they are simply astonishing, the universe playing echoes of its own fireworks. Then there are the unexpected signals. Webb has detected faint transient flashes that defy quick explanation. Some may be flares from active black holes, others could be collisions of neutron stars or exotic stellar remnants. A few are so brief and unusual that they remain unidentified. Each one sparks debate artifact or anomaly noise or new physics. For now, they are logged and monitored mysteries waiting for repetition. Even the beauty of Webb's images can feel unreal. The pillars of creation, long made famous by Hubble, appear under Webb's gaze like a sculpture of glowing glass. Every filament of dust shines, every newborn star is revealed, and the once shadowed columns now blaze with life. The effect is almost painterly, as though nature itself were creating art on the grandest canvas. Webb's detail turns metaphors into reality. Where we once spoke of mountains of gas or oceans of dust, now we see them etched in infrared light. These surreal moments matter. They remind us that science is not only about equations and models, it is also about wonder. Each image, each echo, each inexplicable flicker is both a clue and an invitation. The universe is stranger than we assume, and Webb's task is to show us just how strange. Yet even amid the surreal there is discipline. Every illusion becomes a measurement. Every echo becomes a data point. Every beautiful image hides layers of spectra and calibration. Behind the artistry lies the rigor of physics. Webb does not merely astonish, it quantifies. That is what makes its surprises so powerful. They are not fantasies but facts demanding explanation. And as Webb continues to gather data, the mysteries accumulate. They will shape the questions of the next decades. What are these transients? How common are time-delayed supernovae? What do lensing illusions tell us about the unseen skeleton of the cosmos? Each question pushes us further from the surreal into the fundamental. From galaxies too old to stars too fast to worlds with exotic skies, Webb's revelations form a mosaic of paradoxes. And soon as we approach the conclusion of its first chapter, the question becomes larger still. What does all of this mean for our place in the cosmos? Every spectrum Webb records, every galaxy, it reveals every planet it dissects, brings us closer to the ultimate question. What does this mean for life? Not just life somewhere else, but life here, and the meaning of being alive in a universe so vast and strange. For centuries, humanity has asked whether we are alone. The night sky seemed endless yet unreachable. Then came the discovery of exoplanets, first a handful, then thousands. Now Webb has transformed those dots into worlds with character chemistry and weather. We're no longer asking whether planets exist, but whether any of them breathe. The detection of molecules like water vapor, methane, and carbon dioxide in distant atmospheres changes the scale of the question. It means we can test, not guess. For the first time, the ingredients of habitability are measurable across light years. Even tentative hints of more complex compounds like the controversial case of dimethyl sulfide on K2SUN-B shift the conversation. These are not proofs of life, but they are proof that we have the tools to search with rigor. The implications stretch beyond science. If Webb were to confirm a true biosignature, the discovery would reshape philosophy, religion, and culture. It would tell us that life is not unique to Earth, that the spark of biology is woven into the fabric of the cosmos. Even if no biosignature is ever found, the act of searching enlarges our perspective. It forces us to see Earth as one planet among many fragile yet connected to a greater whole. Webb also reframes time by revealing galaxies that matured quickly, black holes that grew in a rush, and stars that enriched space earlier than expected. It suggests that the conditions for planets, and perhaps life, may have arisen sooner than we thought. Life may not be a latecomer in the universe. It may be part of the story from very early on. That possibility, even if unproven, alters how we imagine the cosmic timeline. Yet there is humility in these discoveries. Webb shows us how little we know, how often our models fall short, how easily the universe resists our neat categories. Every answer comes wrapped in more questions. Life, if it exists elsewhere, may be stranger than we can anticipate, or it may be common, ordinary, hidden in plain sight. The only way forward is to keep looking. The telescope itself becomes a symbol, a mirror of gold stationed far from Earth, patiently absorbing the faintest whispers of light. It is a machine built by human hands, but its gaze extends across cosmic history. It reminds us that curiosity is our defining trait that we reach. Not because the answers are easy, but because the questions are irresistible. And as Webb continues to return its data, we find ourselves on the threshold of transformation, not only of cosmology but of self-understanding. To know whether the universe is fertile or barren, whether we are unique or typical, is to confront the deepest dimensions of existence. Webb has not answered those questions yet, but it has made them practical, testable, urgent. From here, the journey broadens. The telescope will keep watching galaxies, stars, and planets. But the deeper story is about us, about what we do with the knowledge, how we adapt our view of reality, and how we carry that vision into the future. Webb is still young. Its mission has only just begun. Yet it has already unsettled cosmology, revolutionized exoplanet science, and transformed our view of the solar system. The future promises even more. Over the next decade, a series of large surveys and coordinated programs will turn Webb from a source of isolated surprises into a systematic explorer, mapping the universe with precision. One of the flagship efforts is JD's the JWST Advanced Deep Extragalactic Survey. This program is pushing the telescope to stare into carefully chosen regions of the sky for hundreds of hours, building images so deep that even the faintest galaxies emerge. These data sets will serve as a reference library charting the growth of galaxies across cosmic time. Alongside JD's, the Cosmic Evolution Early Release Science program known as CEERS is already producing results showing how galaxies clustered, merged, and evolved in the first billion years. Future extensions of these surveys will refine the picture testing models of dark matter, dark energy, and star formation, with a completeness no previous telescope could achieve. For exoplanets, Webb will embark on comparative studies across dozens of worlds. The goal is not only to detect water or carbon dioxide here and there, but to build a taxonomy, a classification system that links atmosphere types to planet sizes, star types, and orbital distances. Over time, patterns will emerge. We will learn which kinds of planets tend to retain thick atmospheres, which lose them, which are rich in organics, and which are barren. Such a framework will guide the search for truly Earth-like worlds with the best chance of habitability. In the solar system, Webb will continue to monitor icy moons like Europa and Enceladus, tracking plumes and surface chemistry that may hint at subsurface oceans. It will watch comets as they release gas and dust, providing clues to the building blocks of our own planet, and it will probe the outer Kuiper belt, mapping the strange frozen remnants of the early solar system. Each of these observations will not only reveal local secrets, but also connect to broader themes of planetary formation and habitability. Perhaps most exciting is how Webb will work with future observatories. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will provide wide-field surveys of galaxies and dark energy, complementing Webb's deep, narrow view. Together they will bridge scales from panoramic maps to forensic detail. Later ground-based giants like the extremely large telescope in Chile will take Webb's targets and examine them with even higher resolution, in visible and near-infrared light. And beyond them lies the dream of the Habitable Worlds Observatory, a proposed mission designed specifically to detect Earth-like planets and search for biosignatures. Webb is the bridge to that future, proving the methods and preparing the way. All of this requires patience. Webb is not a single burst of discovery, but a long campaign. Its orbit at the second Lagrange point is stable, its instruments cooled and protected by the vast sun shield. With careful management of fuel, engineers expect it to last 2 decades or more. That means a generation of astronomers will grow up with Webb as their constant companion, shaping the field for years to come. Already the early data have changed textbooks. In 10 years, the transformation will be even deeper. Webb will have mapped thousands of galaxies at extreme distances, characterized hundreds of exoplanet atmospheres, and traced the cycle of stars and elements in exquisite detail. Its discoveries will not only answer questions, but also generate new ones, ensuring that the spirit of curiosity continues. The telescope itself may be silent, but its impact will echo for decades. And even as Webb continues to work, we can begin to ask, what comes after? How will the next generation of observatories build on its legacy? And what new mysteries will they uncover? Every great observatory leaves a legacy. Hubble gave us the pillars of creation, the deep field, and a vision of the cosmos as a vibrant, expanding tapestry. But Webb's legacy will be different. It will not be defined by a handful of iconic images, though it already has those. It will be defined by a shift in what astronomy itself can do. Before Webb, many questions were out of reach. How did galaxies assemble in the first few 100 million years? How fast did black holes grow? What molecules fill the skies of alien worlds? These were topics for theory speculation and debate. Now they are subjects of direct measurement. Webb moves astronomy from the era of inference into the era of evidence. Its data are not just pretty pictures. They are numerical fingerprint spectra that carry chemistry, physics and history across unimaginable distances. This changes the relationship between humans and the universe. For most of history, the stars were lights we could only admire. With Webb, they are laboratories. We can dissect them, weigh them, read their atmospheres. We can watch the cycle of elements from birth in stars to incorporation into planets. In doing so, we see ourselves more clearly because the carbon in our bodies and the oxygen in our lungs were forged in the processes Webb observes. The telescope is not only looking outward, it is holding up a mirror to our own origins. Webb's long-term impact will also be educational. Generations of students will learn astronomy through its data sets. Future scientists will cut their teeth analysing Webb spectra, just as earlier ones learned with Hubble. Its archives will live on long after the telescope itself has ceased to operate a treasure trove for discoveries not yet imagined. Even decades from now, researchers will mine Webb's data for insights missed in the first rush of excitement. Culturally, Webb has already redefined how we imagine space. Its golden mirror has become an icon instantly recognisable, a symbol of human ingenuity and curiosity. Its images, released in global broadcasts, inspire awe far beyond the scientific community. They remind us that exploration is not only about rockets and astronauts, but also about light patience and vision. Webb has made astronomy a shared story accessible to all. Most profoundly, Webb expands the boundaries of what it means to observe. It shows us that distance is no longer a barrier. Light that began its journey before Earth existed can now be collected, split and understood. The act of observation becomes an act of time travel, reaching into epochs we can scarcely imagine. With Webb, humanity has extended its senses across most of cosmic history. That accomplishment will stand as one of the great milestones of our species. And yet Webb is only the beginning. Its discoveries will shape the design of future telescopes, more specialized, more ambitious. Each successor will build on its foundation, pushing deeper, sharper, broader. Webb's legacy will not only be what it saw, but what it enabled: a cascade of new missions, new questions, new horizons. But as we move toward the conclusion of Webb's story, another question lingers. What does all of this mean for us here and now on our small blue planet? How should we carry the knowledge that the universe is older, richer, and more mysterious than we imagined? That reflection will shape the closing chapters of Webb's tale. The James Webb Space Telescope is more than an instrument. It is a time machine, a storyteller, and a mirror. It has shown us galaxies, 2 old stars, 2 young planets with skies we never imagined and mysteries we still cannot explain. Every image, every spectrum, every surprise has carried us deeper into the truth of the cosmos. That it is stranger, richer, and more alive than we dare to believe. And yet the greatest revelation may not be about the universe at all, but about us. We are a species that builds golden mirrors to catch ancient light. We are creatures of dust who have learned to read the stars. Against the immensity of space, our existence is fleeting, but our curiosity stretches across billions of years. That curiosity is our legacy. Webb has not given us final answers. It has given us better questions. It has turned the unknown into a frontier, not a void. It reminds us that discovery is never finished, that every ending is the beginning of another journey. So as Webb continues its silent watch in the cold of space, remember this. The light it gathers is not only a message from distant galaxies, it is a message to ourselves that we are capable of reaching beyond fear, beyond conflict, beyond the horizon of our small world, to touch the infinite and to know that we are part of it. Thank you for joining me on this voyage. The universe still has secrets to share, and together we will keep listening. For as long as humans have looked up at the night sky, one question has burned brighter than the stars themselves. Are we alone? In ancient times, it was a matter for myth and philosophy. Some imagined gods walking among the constellations, others believed Earth was the only world unique and isolated. But as centuries passed and science replaced myth with measurement, the question did not fade. It grew sharper, more urgent, because the universe kept growing around us. 400 years ago, Galileo lifted a telescope and found moons orbiting Jupiter. Suddenly, Earth was not the centre. 2 centuries later, astronomers saw faint stars wobble and realised they might host planets. By the 20th century, spacecraft had flown past every world in our solar system, and yet not one showed unambiguous signs of life. Mars was dry, Venus was a furnace. The outer moons, though intriguing, remained beyond reach. The silence deepened the mystery. Then came the revolution. In the 1990s, using delicate measurements of starlight, astronomers confirmed the first planets orbiting other suns. They were nothing like Earth gas giants orbiting scorchingly close to their stars, hot Jupiters defying all expectations. But the discovery changed everything. If planets existed elsewhere, then Earth could not be the only one. The universe might be crowded with worlds. The count grew quickly. With improved instruments, thousands of exoplanets were discovered, ranging from small rocky worlds to giant planets bigger than Jupiter. Some orbited stars like our own sun, others circled dim red dwarfs. A few lay in the so-called habitable zone where temperatures could allow liquid water. For the first time, the idea of life beyond Earth shifted from speculation to calculation. We now had statistics, probabilities, catalogues of worlds that might be living or lifeless. And yet numbers alone are not enough. To know whether a planet can host life, we must look at its atmosphere. Gases can betray the presence of biology: oxygen, methane, water vapour. When found together in disequilibrium, they whisper of processes beyond geology. The problem was that earlier telescopes were not powerful enough. Hubble could glimpse atmospheres in broad strokes, but it could not disentangle the details. We needed a new eye, sharper and steadier, tuned to the wavelengths where these molecules leave their fingerprints. That eye is James Webb. With its golden mirrors and infrared vision, Webb can capture the faint light of a planet passing in front of its star, and from that light read the chemistry of alien skies. For the first time in history, we have an instrument capable of searching for the signatures of life, not in our solar system, but across the galaxy. This is the turning point. The question that haunted philosophers, inspired poets, and drove explorers has become an experiment. We can measure it. We can test it. We can begin to answer not with stories but with spectra. And so the search begins. From the glowing giants of distant systems to the quiet, temperate worlds that might resemble our own, Webb has opened a doorway into the most profound investigation humanity has ever attempted: the hunt for alien life. When the first exoplanets were confirmed, many expected that signs of intelligent life would follow quickly. The logic seemed simple. If there are countless stars and many of them have planets, surely some of those planets must host civilizations. And if civilizations exist, would they not send signals, perhaps radio broadcasts echoing across the galaxy? This idea gave rise to one of the boldest scientific efforts of the 20th century, SETI, the search for extraterrestrial intelligence. The method was straightforward in concept. Astronomers would point radio telescopes at the sky and listen. If an advanced civilization was transmitting intentionally or accidentally, we might pick up a faint whisper. After all, Earth itself leaks radio noise into space. Television signals, radar beams, communication chatter. If we do it, why not them? The earliest searches in the 1960s targeted nearby stars. They were limited, listening only to narrow ranges of frequency. The results were silent. decades passed and the silence deepened. Larger projects followed: the giant Arecibo dish in Puerto Rico, the Allen Telescope Array in California. International collaborations scanning millions of frequencies simultaneously. Yet the outcome was always the same. No confirmed signals, only occasional bursts of noise later traced to natural phenomena or earthly interference. The silence was unsettling. It was summarized in the famous Fermi paradox. If the galaxy is filled with life, where is everyone? With hundreds of billions of stars, even a tiny fraction producing civilization should have filled space with chatter. Instead, our telescopes heard only the hiss of cosmic background radiation. Some scientists argued this silence was meaningful. Perhaps intelligent life is rare, fleeting, or chooses not to broadcast. Others suggested we may not be listening correctly. What if alien civilizations communicate with technologies we cannot yet imagine? What if their signals are encrypted, hidden, or so different from our own that we mistake them for noise? The possibilities are endless, but the evidence remains absent. Despite the silence, SETI taught us something vital. The search for life cannot rely solely on waiting for others to call. We must learn to recognize life indirectly through its impact on planets and atmospheres. The chemistry of a sky does not need to intend communication. It simply exists. Oxygen from forests, methane from microbes, carbon dioxide cycles, water vapor from oceans. These are signatures that any telescope tuned properly can read. This realization shifted the focus from intelligent signals to biosignatures. Instead of hoping for alien broadcasts, we now look for alien biology. And here James Webb enters the stage. Where radio telescopes listen for deliberate voices, Webb observes the unintentional breath of life itself. It does not wait for a message, it reads the sky. The lessons of SETI still matter. They remind us that the universe may not be eager to reveal itself, that discovery may require patience and persistence, but they also remind us that silence is not emptiness. Silence may simply mean we have not yet learned the right way to listen. Webb gives us that new way, and so the story moves forward from radio whispers to infrared spectra, from listening to light. The question remains the same, but the methods have evolved. Humanity is no longer just an eavesdropper on the cosmos. With Webb, we are investigators examining worlds themselves for the traces of breath chemistry and life. The discovery of exoplanets was not just a milestone, it was an earthquake in astronomy. For centuries, the existence of other worlds was a matter of speculation. Then suddenly, in the last few decades, planets began to appear everywhere. The revelation was as if the universe had been hiding a vast population waiting for us to build instruments sensitive enough to notice. The first confirmed detections in the 1990s stunned astronomers. One planet circled a pulsar, the dense spinning corpse of a dead star. It was a bizarre place for a planet to exist, and yet there it was. Soon after, the first hot Jupiter was found a gas giant orbiting so close to its star that a year lasted only a few days. No one had predicted such a world. The discovery shattered theories of planetary formation. As more planets were detected, the diversity became overwhelming. There were super-Earths larger than our planet, but smaller than Neptune. There were mini-Neptunes, icy worlds with thick envelopes of gas. There were lava worlds with molten surfaces glowing under the heat of nearby suns. Some planets orbited double stars like Tatooine from science fiction. Others traced eccentric paths swinging wildly closer and farther from their stars. The universe, it turned out, was more imaginative than our textbooks. The Kepler Space Telescope transformed the field. By staring at a patch of sky for years, it recorded tiny dips in starlight as planets crossed in front of their stars. Kepler revealed thousands of worlds showing that planets are not rare. They are the rule. Practically every star hosts at least one. Many stars have entire systems, some with architectures stranger than anything in our own neighbourhood. From this flood of data, astronomers began to classify. Planets were grouped by size, orbit, and composition. Rocky Earth-sized planets, gas giants, sub-Neptunes, worlds in the habitable zone where conditions might allow liquid water. But classification was only the first step. To understand whether these worlds could host life, we needed to move beyond counting and start characterizing. What were their atmospheres made of? Did they have oceans, clouds, or storms? Did they carry the chemical imbalances that suggest biology? That is where James Webb enters the story. While Kepler and its successors reveal the sheer abundance of planets, Webb provides the detail. It can take those silhouettes against starlight and transform them into spectra lines and patterns that reveal chemistry. Instead of just knowing a planet exists, we can begin to know what it is like. This shift changes everything. No longer are exoplanets dots on a chart. They become places, worlds with weather history and potential. Some are scorching, some frozen, some tempestuous, some calm. Each one is a laboratory in the grand experiment of nature. Each one is a chance to ask, could life take root here? And among this multitude of worlds, Webb has already found targets that capture the imagination. A hot Jupiter with sulfur dioxide clouds, a sub-Neptune with methane and carbon dioxide, a world where hints of exotic molecules appear faint and fragile yet suggestive of something more. These first results are only the beginning. The catalogue is vast and Webb has years ahead to explore it. The search for life is no longer about Earth alone. It is about context, about seeing our planet as one data point among thousands. And as the list grows, the odds shift. Life may not be rare. It may be common, written into the physics of chemistry and starlight. We do not know yet, but for the first time we have the means to find out. To search for life, we must learn to read the skies of distant worlds. This is where James Webb excels, using a technique both elegant and powerful: transmission spectroscopy. The method begins when a planet passes directly in front of its star. As it transits, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. That light carries information etched with the fingerprints of molecules. Every gas absorbs specific wavelengths. Water vapor leaves dips in one part of the spectrum, methane in another, carbon dioxide in yet another. By spreading the light into a rainbow and analysing the faint variations, astronomers can deduce the chemical composition of alien skies. It is as though the planet is whispering its secrets and Webb is trained to listen. The challenge lies in precision. The effect of an atmosphere on starlight is minuscule, often less than a fraction of a percent. Earlier telescopes like Hubble and Spitzer could attempt these measurements, but their data were noisy, their resolution limited. Webb's infrared instruments, stable and exquisitely sensitive, change the game. They can detect the smallest wiggles in a spectrum, turning uncertainty into clarity. One of Webb's first triumphs came with the hot gas giant WASP 13b. Observations revealed a rich spectrum, not only water vapor but also carbon dioxide and sulfur dioxide. The latter was especially striking as it was the first clear detection of photochemistry on an exoplanet. Starlight interacting with the atmosphere had produced new molecules reshaping the chemical landscape. It was proof that Webb could not only detect gases but also witness chemistry in action. Another landmark was K2-18b, a sub-Neptune orbiting in the habitable zone of a red dwarf star. Webb's data showed methane and carbon dioxide with tentative signs of dimethyl sulfide, a compound on Earth, produced primarily by marine plankton. The detection is debated, uncertain but electrifying. Even the hint that Webb could glimpse such a molecule across light years shows the leap we have made. These results confirm the power of the method. For the first time, we're not only detecting exoplanets, but describing them in detail. We know their skies contain water, carbon, sulfur, and perhaps more exotic chemistry. Each new spectrum is a step toward identifying worlds that may carry the breath of life. And this is only the beginning. Webb will apply transmission spectroscopy to dozens of planets. Hot Jupiters, warm Neptunes, rocky super-Earths. Some will reveal thick atmospheres shrouded in clouds. Others may show bare rock stripped of gases by stellar winds. Each outcome teaches us something about habitability, about what makes a planet stable, fragile, or alive. To imagine what comes next is staggering. One day, perhaps not far, a spectrum may arrive that shows oxygen alongside methane, or water alongside ozone. A chemical imbalance hard to explain without biology. That would be the moment the search for life moves from possibility to detection. Webb has not reached that milestone yet, but it has opened the path. From a faint dip in starlight across unimaginable distances, we're learning to read the invisible. It is science at its most delicate and its most profound. To claim we have found life is no small thing. The universe is filled with processes that can mimic biology, and every molecule we search for has both living and non-living origins. That is why astronomers tread carefully. They speak not of proof, but of biosignatures, chemical clues that taken together may point toward biology. The classic example is oxygen. On Earth, oxygen is abundant only because plants and microbes constantly produce it. Left alone, it would quickly bind with rocks or escape into space. Finding oxygen in an alien atmosphere would be exciting. But oxygen can also arise from non-biological processes such as ultraviolet light breaking apart water molecules. By itself, it is suggestive but not decisive. Methane tells a similar story. On Earth, much of it comes from microbes, but volcanoes and chemical reactions deep underground can produce it too. The real power lies not in individual gases, but in combinations. When oxygen and methane coexist in large amounts, they are unstable together. One should destroy the other. Their simultaneous presence implies something is replenishing them, a disequilibrium that on Earth biology maintains water vapor, carbon dioxide, nitrous oxide, ozone. Each has its own story, its own pitfalls. What scientists seek are patterns, ensembles of gases that defy easy geological explanations. It is less about spotting a single molecule and more about reading the balance of a planet's atmosphere the way a doctor reads vital signs. The patient may not speak, but the body reveals the truth. This is why Webb's results are so important. For the first time, we can measure these gases with the precision required to test for disequilibrium. We can ask whether a planet's chemistry is stable or out of balance. We can begin to separate the possible from the probable. Already in the tentative hints from K2-18b, we see the potential of this approach. Even a disputed detection of dimethyl sulfide is enough to change the conversation. It shows that biosignature science is no longer theoretical. It is operational. Yet caution remains. Astronomers know the dangers of false positives. A planet with unusual geology or bathed in the radiation of an active star could mimic life's chemistry. That is why multiple observations, repeated transits, and cross-checks with other instruments are essential. One spectrum can be a tease. Many spectra consistent and clear can build a case. The quest for biosignatures is a slow, careful process, more like a trial than a revelation. But it is also thrilling. For the first time, humanity is gathering the evidence required to argue the case for life beyond Earth. Each observation is a piece of testimony, each gas a witness. And beyond the science lies the anticipation. Imagine the moment when a spectrum arrives and the pattern is undeniable. Oxygen, methane, water, and disequilibrium across light years of space. No announcement in history could carry greater weight. Webb has not given us that moment yet. But it has brought us to the threshold where the possibility is real. The question is no longer whether we can search for life. It is how we will interpret the answers when they come. When we imagine life beyond Earth, it is tempting to picture another blue planet with oceans, forests, and skies like our own. But the universe may not be so narrow in its creativity. Life could arise in forms unfamiliar, built on chemistries and conditions we have barely considered. To search only for copies of Earth would be to limit our imagination. On Earth, life is based on carbon. Carbon's ability to form complex, stable molecules makes it ideal for biology. But could silicon play a similar role elsewhere? Silicon abundant in rocks and sand also bonds with multiple elements. In theory, silicon-based life could exist, though its molecules tend to be less flexible than carbon's. Perhaps in environments hot enough to keep silicon compounds fluid, some form of alien metabolism could emerge. Water too is central to our definition of life. It dissolves chemicals, carries nutrients, and stabilizes temperatures. But water is not the only solvent in the cosmos. Ammonia, methane, or even sulfuric acid could play similar roles under the right conditions. Saturn's moon Titan, with its methane lakes and nitrogen atmosphere, offers a glimpse of this possibility. If biology can arise in such exotic chemistry, Webb's instruments might detect unusual gases or spectral features that betray its presence. Even within carbon, water life diversity is immense. Microbes thrive in boiling springs, in the crushing darkness of the deep ocean, in acidic pools, and even inside rocks. Life on Earth has colonized extremes once thought impossible. If Earth can harbor such resilience, what might alien worlds achieve? A planet scorched by radiation might evolve organisms with protective pigments. A frozen moon might shelter subsurface oceans warmed by tides. Biology is resourceful and evolution relentless. For Webb, this means keeping an open mind. The telescope does not know what life is. It only measures light, but in that light may be hints of chemistries we do not yet understand. An atmosphere rich in unexpected compounds, or a spectrum that refuses to match our models, could signal not an error, but a new kind of biology. Recognizing it will demand both caution and creativity. This is why scientists often speak of agnostic biosignatures, signals that indicate complex processes, even if we cannot immediately identify them as familiar life. Patterns that defy simple physics or geology may be the fingerprints of something new. Webb may not deliver proof, but it can deliver anomalies. And anomalies are where discovery begins. The great lesson of astrobiology is humility. Life may be stranger than our stories, stranger even than our science. The search is not about confirming Earth's uniqueness, but about testing whether nature has written many versions of biology across the cosmos. And in this search, Webb is our first great tool. It gives us the ability to ask with data rather than dreams. Is there only one way to be alive, or are there countless? The search for life is not only about single discoveries, it is about building a framework, a map of possibilities that tells us where to look and what to expect. Before Webb exoplanets were mostly catalogued as points of data, a size and orbit, perhaps a rough mass. Now with Webb's precision, we can begin to sort them into categories defined not only by physics, but by chemistry and climate. Hot Jupiters were the first exoplanets to dominate discoveries. Massive gas giants orbiting perilously close to their stars, they are blasted by radiation. Their atmosphere swollen and turbulent. Webb has revealed the fine details of these giants. Winds roaring at thousands of kilometers per hour, chemical cocktails of carbon dioxide, sodium sulfur dioxide, and even glassy silicates. They are hostile, uninhabitable, yet essential. They test our models of atmospheric dynamics under extreme conditions. Further out are warm Neptunes and sub-Neptunes, smaller gas or ice giants that often defy comparison to anything in our solar system. Many of them have thick atmospheres, but Webb's spectra are beginning to distinguish which are hazy, which are clear, and which might contain traces of water vapor or methane. These worlds may not host life as we know it, but they are laboratories for understanding how planets retain or lose their gases. Then come the rocky super-Earths planets, larger than Earth but smaller than Neptune. These are among the most tantalizing because their size suggests solid surfaces and potential atmospheres. Webb's instruments are already probing some of these worlds, though clouds and hazes often veil their spectra. Even so, the effort marks a step closer to the Holy Grail, an atmosphere rich in water oxygen or methane around a rocky planet in the habitable zone. Among red dwarf stars, the most common in the galaxy, Webb is targeting small planets where conditions might allow liquid water. These stars are dim, making their planets easier to study in transit. They are also volatile blasting flares that may strip atmospheres or sterilize surfaces. Webb's data will help us learn which red dwarf planets are resilient and which are doomed. A key question since billions of them dot the Milky Way. Together, these studies are not random. They are building a comparative atlas of planets. Just as biologists classify species to understand evolution, astronomers classify planets to understand habitability. Which combinations of mass, orbit and atmosphere create stable climates, which lead to runaway greenhouses or frozen wastelands. Where does Earth fall in this spectrum and how rare or common is it? This is the heart of Webb's role. It transforms the exoplanet field from a list of curiosities into a science of patterns. Once patterns are clear, predictions follow. We will not only know what kinds of planets exist, but also where to focus the search for life. And as those patterns emerge, a new question arises. If planets like Earth exist, how do we recognize the truly special ones? The worlds that not only could host life, but perhaps already do. The phrase habitable zone has become almost mythical. It is the ring around a star where a planet could in theory sustain liquid water on its surface. Too close and water boils into steam. Too far and it freezes into ice. Within this Goldilocks zone, conditions may be just right. It is the simplest and most powerful filter astronomers use when scanning thousands of worlds. Water is central because on Earth it is the universal solvent of life. It carries nutrients, supports chemistry and shapes climates. Without liquid water, life as we know it struggles to take hold. That is why the habitable zone is often called the life zone. Webb targets many of these planets hoping to read their atmospheres for signs of water vapor, oxygen or methane. But habitability is not as simple as distance. A planet in the right zone may still be barren. Venus orbits within the Sun's habitable zone, yet its atmosphere has turned it into a hellscape of sulfuric acid clouds and crushing heat. Mars just on the outer edge once had rivers and lakes, but its thin atmosphere let its oceans escape. Position matters, but so do mass geology, magnetic fields and atmospheric stability. Webb's role is to refine the concept. By studying planets across different zones and comparing their atmospheres, it teaches us that habitability is a spectrum, not a switch. Some planets may hover on the edge, teetering between stability and collapse. Others may cycle between wet and dry eras. Webb's instruments can detect these subtle differences, showing that being in the habitable zone is a beginning, not a guarantee. What this means is profound. Earth-like conditions may be rare even among Earth-like orbits. The life zone is a necessary filter, but not the final word. We must look deeper past the orbit into the sky itself. The paradox becomes clear when we compare planets. Some lie squarely in the habitable zone, yet are hostile. Venus should be temperate, but its greenhouse effect is catastrophic. Mars should be marginally habitable, but its lack of atmosphere left it dry and cold. Meanwhile, moons like Europa and Enceladus orbit far outside the Sun's habitable zone, yet they may harbour oceans beneath icy shells warmed by tidal flexing. The rulebook is more complicated than we thought. This is why Webb's mission is not only to confirm theories, but to challenge them. Its infrared eyes can probe for water vapour even in unexpected places. It can detect carbon dioxide in thin atmospheres or identify hazes that trap heat. By expanding our survey beyond the textbook life zones, Webb reminds us that habitability is creative. Life may find ways to exist in niches far stranger than Earth. Consider red dwarf stars. Their habitable zones are tight and close. Planets there risk tidal locking, with one side scorched and the other frozen. Yet if an atmosphere circulates heat efficiently, such a world could still support oceans. Webb will test these possibilities, searching for balance where physics suggests extremes, or consider rogue planets wandering through space without stars. By traditional definitions, they should be sterile. But if they carry thick atmospheres or internal heat, could they hide warm environments beneath? Webb may never detect life on such worlds directly, but its discoveries force us to expand our imagination. The lesson is clear. The habitable zone is a guidepost, not a verdict. Life may thrive outside its borders and planets within it may perish. What matters most is not distance, but the delicate balance of atmosphere, chemistry, and energy. Webb is teaching us to stop looking only for Earth's twin, and to start looking for Earth's cousins, diverse, imperfect, but still alive. The search for biosignatures is as thrilling as it is treacherous. Each molecule detected in an alien atmosphere carries the promise of discovery, but also the danger of misinterpretation. The universe is clever at disguising geology as biology, and the line between the two is razor thin. Take oxygen, for example. On Earth, its abundance is sustained by photosynthesis. Without life, it would vanish from our air in a geological blink. So astronomers long assumed oxygen would be the smoking gun of alien biology. But Webb's work, combined with theoretical models, reminds us of caution. Ultraviolet radiation can split water molecules, allowing hydrogen to escape into space, while oxygen accumulates. A dead, desiccated world could masquerade as alive. Methane offers another puzzle. On Earth, microbes are prolific methane producers, but volcanoes, hydrothermal vents, and chemical reactions in a planet's mantle can also release it. Finding methane alone is not enough. Even methane with carbon dioxide is not decisive, because geologic activity can mimic that pairing under certain conditions. Only when multiple gases coexist in unstable equilibrium do the odds tilt toward biology. The case of K2-18b shows this dilemma perfectly. Webb's data hinted at methane, carbon dioxide, and even traces of dimethyl sulfide, a compound that on Earth is tied almost entirely to life. The announcement sparked excitement, but also skepticism. The signal was faint on the edge of detection. Noise clouds or unexpected atmospheric chemistry could explain it. Scientists stress that more observations are needed, and the debate continues. This is science at its core, cautious, incremental, but daring. A single spectrum can inspire headlines, but Webb's role is to build evidence to repeat observations until patterns emerge. Biosignatures are not about one molecule in isolation. They're about ensembles, balances, disequilibria that defy geology, and even then interpretation requires humility. False positives are only half the problem. There's also the risk of false negatives. Life may exist, but in forms we do not recognize. Its chemistry may not announce itself in oxygen or methane. It may use molecules we consider inert or operate in solvents other than water. To dismiss a world as sterile simply because it lacks our familiar gases could be just as misleading as declaring life too soon. Webb's task, then, is not to deliver a final verdict, but to map the possibilities, to show us which planets deserve more attention which atmospheres whisper of imbalance, which signals demand deeper scrutiny. It provides the clues, but the interpretation will be a generational effort weaving together astrophysics, chemistry, and biology. The thrill lies in the uncertainty. Each new detection is both a promise and a puzzle. Are we glimpsing biology across light years, or merely the tricks of geology under alien suns? The answer will not come easily, but for the first time we have the tools to ask the question seriously, and that alone is revolutionary. Not every spectrum Webb collects fits neatly into our expectations. Alongside the triumphs of clear detections come puzzles, strange patterns, unusual signals, data that resist easy interpretation. These anomalies remind us that discovery is not only about confirming what we predict, but also about confronting the unexpected. Some of these mysteries come from the atmospheres of exoplanets. Webb has detected hazes that are thicker than models predict masking signatures of gases we expected to see. On certain hot Jupiters, the clouds appear to be laced with exotic particles, silicates metals creating spectra that look nothing like Earth's skies. On others, the atmosphere seems strangely muted, their features flat and ambiguous, as if something is erasing the chemical fingerprints before they reach us. Are these planets shrouded in global smog, or do they represent a chemistry we have yet to model correctly? Even more intriguing are the faint fleeting features. In some cases, Webb has caught glimpses of absorption lines that hint at unusual molecules, compounds that on Earth would be unstable or rare. These detections are tentative, hovering at the edge of certainty, but they tease the imagination. Could they represent exotic photochemistry under alien suns? Or are they simply noise masquerading as signal? The line is thin and only repeated observations can decide. Occasionally, Webb's data have revealed atmospheric dynamics that defy expectations. Some planets show winds so powerful that heat is redistributed in patterns our models cannot yet explain. Others show temperature inversions where upper layers are hotter than lower ones, contrary to what theory predicts. These quirks remind us that every atmosphere is a laboratory, and many do not obey Earth's rules. Beyond exoplanets, Webb's deep field surveys have also turned up the unexpected. Galaxies appearing older, brighter, or more massive than models allow. Star formation rates that seem impossibly high. Quiescent galaxies that look dormant when they should still be alive with activity. Each one is a challenge to cosmology, but also a clue. Perhaps our models are incomplete. Perhaps the universe has tricks we do not yet understand. And then there are the transients, brief flashes of light, unexpected brightenings or sudden dimmings. Some may be supernovae or active black holes. Others remain unexplained. Webb is sensitive enough to capture signals that no other telescope can confirm, leaving astronomers with tantalizing data points that resist classification. What unites these anomalies is possibility. In the past, strange results were often dismissed as errors. Now with Webb's precision, they demand attention. Each unexplained feature may be the seed of a new discovery, an invitation to rethink assumptions. They remind us that the universe is not obligated to match our expectations. It writes its own story, and sometimes that story surprises us. These puzzles are not failures. They are the frontier. Every mystery Webb reveals expands the space of questions we can ask. And in those questions lies the future of discovery. The true power of Webb lies not only in single discoveries but in comparisons. A lone spectrum can be intriguing, even breathtaking, but its meaning grows richer when placed beside dozens of others. Patterns begin to emerge and patterns tell stories. Through comparison, Webb is transforming the study of exoplanets from a collection of curiosities into a coherent science. Already astronomers are assembling catalogues of spectra from hot Jupiters, warm Neptunes and rocky super-Earths. When viewed together, the similarities and differences stand out. Some hot Jupiters show clear signatures of water and carbon dioxide, while others are muted by hazes. Some sub-Neptunes appear cloaked in thick atmospheres, while others seem stripped bare. Even among planets of similar size and orbit, the diversity is staggering. This diversity is not random. It encodes the history of each world. A planet rich in carbon dioxide may have undergone volcanic outgassing. One with sulfur dioxide could be shaped by intense stellar radiation. A planet with water vapor might hint at oceans below. By comparing many planets, Webb allows scientists to test which factors matter most: the type of star, the planet's mass, the distance from its sun, or the violence of its past. This comparative approach is essential to the search for life. We cannot know in advance which conditions are truly hospitable, but by mapping the full range of planetary atmospheres, we begin to see the boundaries of possibility. If water vapor is common, then potential habitability may be widespread. If methane is rare, perhaps biology is too. Each new world adds a point to the graph, tightening the constraints on what life requires. It also reframes Earth. In isolation, our planet is special, filled with oceans, oxygen, and life. But in context, Earth becomes one data point among thousands. By studying exoplanets, we learn not only about them, but about ourselves. Why does Earth have stable oceans while Venus boiled and Mars froze? Why did biology flourish here and nowhere else we know? Webb's comparative surveys are a way of answering these questions through cosmic statistics. The telescope's legacy will not be a single planet declared alive or dead. It will be a planetary atlas, a grand map of atmospheric chemistry across the galaxy. From this map, future telescopes can target the most promising candidates, narrowing the search for true biosignatures. Webb is the scout laying the foundation for explorers yet to come, and in this growing atlas there may already be hints of where to look next. Planets that stand out from the crowd, worlds whose chemistry whispers of imbalance, candidates that demand follow-up. The future of the hunt for life will not be about chance, but about strategy guided by the patterns Webb is revealing now. James Webb has opened the door, but it will not walk the path alone. The search for life is a relay, and other instruments are already preparing to take the baton. Together they will turn Webb's hints into certainty, its puzzles into answers, and its discoveries into the foundation for something even greater. The first in line is the Nancy Grace Roman Space Telescope, scheduled to launch later this decade. Roman is not designed to probe individual planets as Webb does, but to survey the sky on a grand scale. Its wide-field vision will reveal thousands of new exoplanets through micro-lensing events where a foreground star magnifies a background one. Roman will also map dark energy with exquisite precision. For exoplanet science, it will provide the statistics, the broad context that Webb's deep but narrow view cannot. On the ground, a new generation of giant telescopes is rising. The extremely large telescope in Chile, with a mirror 39 meters across, will dwarf anything built before. Alongside it will stand the giant Magellan telescope and the 30-meter telescope. These instruments with adaptive optics to sharpen their vision will target some of the planets Webb identifies as promising. They will dissect their atmospheres in visible and near-infrared light, resolving details Webb cannot see. Together, space and ground will work in concert, Webb scouting giants confirming, but the boldest vision belongs to the Future Habitable Worlds Observatory, a mission still in planning but already shaping dreams. Its purpose is clear: to find and study true Earth-like planets. Unlike Webb, which is optimized for many cosmic questions, the Habitable Worlds Observatory will be designed with a singular focus: biosignatures. With coronagraphs or star shades to block the overwhelming glare of parent stars, it will be able to capture direct images of planets like our own. It will not just read their atmospheres in transit, but actually see their reflected light, perhaps even detecting surface features, oceans, or seasonal changes. Webb is the bridge to this future. It proves the techniques, builds the catalogues, and identifies the candidates. Without Webb, the Habitable Worlds Observatory would fly blind. With Webb, it will fly with purpose, guided to the most likely places to find life. The synergy extends further. Missions like Ariel from the European Space Agency will conduct atmospheric surveys of hundreds of planets. Small specialized telescopes will hunt for transits around nearby stars. Each piece adds to the mosaic, making the search for life a truly global endeavor. For humanity, this means the next 2 decades may be the most transformative in the history of astronomy. We will not only know that planets exist, we will know their climates, their chemistry, and perhaps their habitability. And if even one shows unambiguous signs of biology, the discovery will change everything. Not just science, but our sense of place in the cosmos. Webb began the hunt, but it is the first chapter of a longer story, one that will stretch into the future, written by telescopes yet to fly, and questions yet to be asked. Imagine the moment. A spectrum arrives from a distant world and the pattern is undeniable. Oxygen and methane coexisting in disequilibrium water, vapor glistening in the lines, perhaps even other exotic compounds that on Earth are linked to biology. The data are checked, rechecked, debated, confirmed, and then the announcement: we are no longer alone. For science, it would be a revolution on par with Copernicus showing that Earth orbits the Sun, or Darwin revealing the story of evolution. Astrobiology, once a field built on theory, would suddenly have evidence. Every branch of science would engage. Biologists would ask how alien metabolisms function. Chemists would wonder what molecules support them. Astronomers would seek out similar worlds to test whether life is rare or common. Theories of planet formation, climate, and evolution would all need rewriting in the light of this discovery. Religion and philosophy too would feel the impact. For some traditions, confirmation of life elsewhere would affirm the vastness of creation. For others, it might challenge long-held views of humanity's uniqueness. Questions of meaning, purpose, and destiny would be reframed under a cosmic scale. Theologians and philosophers would debate whether intelligence and spirit are universal, or whether life is diverse but consciousness remains rare. For civilization, the effect could be unifying. National boundaries shrink when compared to the gulf of light years. The discovery would belong to no single nation but to all humanity. In a world often divided, the knowledge that life has blossomed elsewhere might remind us of our shared identity as Earthlings. It could inspire a new era of exploration, a renewed sense of purpose, a recognition that we are part of a greater community of the cosmos. Of course, uncertainty would remain. A biosignature is not a handshake. It would not tell us whether the life is microbial or multicellular, intelligent or simple. Yet even the humblest alien microbe would be enough to prove that biology is not unique to Earth. That would imply that life is a natural outcome of chemistry, not a miracle confined to one planet. And if life arises easily, then somewhere intelligence might too. The discovery would not end the search. It would ignite it. And yet we must prepare for the psychological weight of such a revelation. Some might fear it, imagining threats where none exist. Others might dismiss it, clinging to the belief that Earth is singular. But for many it would be awe, the sense that the universe has just grown larger, more alive, more mysterious than ever before. Webb may not be the telescope to deliver that ultimate proof, but it is paving the way, showing us where to look, teaching us how to read the skies. And if the day comes when a planet's spectrum declares beyond reasonable doubt that life breathes beneath alien suns, then Webb will have been the herald of that age. The search for life is no longer the domain of myth or speculation. It has become an experiment, careful, methodical, and breathtaking in scope. James Webb has given us the first tools to probe the skies of distant worlds, to read their atmospheres as if they were books written in light. What was once philosophy has become data. What was once imagination has become measurement. And yet the story is far from finished. Webb's spectra show us diversity, complexity, and mystery. Some worlds whisper of chemistry that hints at oceans. Others puzzle us with signals we cannot yet explain. The telescope has revealed more questions than answers, and in science that is the surest sign of progress. We now stand at a threshold. Ahead lies the promise of new telescopes, new missions, and new generations of explorers. Together they will build on Webb's foundation, mapping planets in detail, perhaps one day capturing the reflection of alien oceans, the shimmer of unfamiliar clouds, or the faint pulse of life itself. But even if no definitive biosignature comes soon, the journey itself has meaning. It shows us that Earth is not alone in being a world of consequence. It reminds us that the universe is not a void, but a tapestry of possibilities. And it forces us to confront the deeper question: if life is out there, what does that make of us? Perhaps we are rare, a singular spark in a vast dark. Or perhaps life is abundant and the galaxy is alive with voices waiting to be heard. Both possibilities are profound. One tells us how precious we are, the other tells us how connected we are. Either way, the universe becomes richer, larger, more alive. So the hunt continues. Webb watches in silence, capturing light that has travelled for centuries, waiting for us to decode its message. Each spectrum is a letter from the cosmos, and somewhere among them perhaps lies the word we long to read. Life. Until then we listened, we wonder, and we keep searching. Thank you for joining me on this journey. The universe is vast, the questions endless, and the adventure has only just begun. Before there were galaxies, before there were planets, before even the familiar stars of the night sky, the universe was dark. It was filled with hydrogen and helium, the simplest of elements drifting in a cosmic fog left behind by the Big Bang. For hundreds of millions of years, nothing stirred that darkness. There were no suns, no moons, no guiding lights, only silence and shadow. This period, known as the Cosmic Dark Ages, was the longest night the universe has ever known. But darkness does not last forever. Tiny ripples in the fabric of space seeded in the earliest moments of creation began to grow under gravity's pull. Clouds of gas slowly collapsed their centers, heating as pressure rose. And then for the first time in cosmic history, the miracle occurred. Fusion, hydrogen ignited, releasing light. The first stars were born, shattering the silence, piercing the darkness. These first stars were unlike any that shine today. They were titans, hundreds of times more massive than the sun. Their lives were brief and violent, burning hot and bright before collapsing in cataclysmic explosions. In their fiery deaths, they forged the heavier elements. Carbon, oxygen, iron, the very building blocks of life. The universe that began simple now began to grow complex. The appearance of these primordial stars marked the dawn of structure. Their light began to ionize the hydrogen fog, transforming the opaque universe into a transparent one. This era, known as rionization, was a cosmic sunrise. Galaxies took shape, clusters of stars bound by gravity, and the architecture of the universe as we know it began to emerge. Yet this dawn remains mysterious. We cannot see it directly with our eyes. The light of those first stars has travelled for more than 13 billion years, stretched by the expansion of the universe into faint infrared glows. Only a telescope like James Webb, with its golden mirrors tuned to the long wavelengths of ancient light, can glimpse them. Webb was built for this very task, to pierce the veil of the cosmic dawn and show us the first sparks of creation. To witness this era is to travel back in time to the first chapter of the universe's story. It is not just about distant galaxies, it is about us. For in those early furnaces were forged the atoms that would one day form planets, oceans, forests, and human beings. The cosmic dawn is our dawn, and so as Webb opens its eye on the deepest reaches of time, is not only looking outward, it is looking backward into the origins of everything. The story of the universe begins with light, but almost immediately that light faded. After the Big Bang, the cosmos expanded and cooled. Protons and electrons combined to form neutral hydrogen and the first radiation. The cosmic microwave background streamed freely through space, but once that afterglow dimmed, the universe entered a long silence. For hundreds of millions of years, there were no stars to shine, no galaxies to gather. This was the age we call the cosmic dark ages. It may sound empty, but this period was full of potential. The universe was not uniform. Tiny fluctuations in density, relics of quantum ripples magnified by inflation, meant that some regions were just a little denser than others. Gravity worked slowly but relentlessly, pulling matter together. Over vast stretches of time, those small seeds grew, forming clouds of gas that would one day ignite as the first stars. For astronomers, the Dark Ages are one of the most elusive chapters in cosmic history. We cannot see them with ordinary light because there was none. The hydrogen fog was opaque to radiation, absorbing and scattering any attempt at illumination. What remains for us are indirect clues. The faint microwave background, the subtle imprints on large-scale structure, and the ghostly shadows cast when the first stars finally ignited. Reconstructing this era is like piecing together a mystery novel with most of its pages missing. Computer simulations fill in the gaps, showing how matter clumped, cooled, and collapsed. Yet simulations must be tested, and for that we need observations. That is where Webb comes in. Its infrared eyes can capture light stretched by more than 13 billion years of cosmic expansion. By peering so deep, it can catch the earliest galaxies just as they emerge from the fog, their light a beacon from the end of darkness. This is no small feat. The light from those first stars is faint, scattered, and often drowned out by closer, brighter galaxies. Webb's sensitivity and resolution make it the first telescope capable of teasing apart these delicate signals. Already in its first deep fields, Webb has revealed galaxies so ancient that their existence challenges our models. Some appear surprisingly massive, formed much earlier than theory predicted. Are we missing a piece of physics, or are these galaxies different from what we imagined? Each detection is a window into the Dark Ages end, the moment when light returned to the cosmos. By studying them, astronomers hope to trace how the first stars formed, how their radiation rionized the universe, and how the scaffolding of galaxies began. In this way, Webb is not just a telescope. It is a time machine reaching across billions of years to illuminate the pages of history we thought forever lost. The cosmic Dark Ages were not empty. They were a gestation, a silence before the first note of a symphony. And with Webb we are hearing the opening chords. When the first stars finally ignited, they were unlike anything that exists today. Astronomers call them population 3 stars, the very first generation of stellar fire. They were born from pure hydrogen and helium, untouched by the heavier elements that would later enrich the cosmos. With no metals to cool the gas, the collapsing clouds formed stars that were enormous giants, hundreds, even thousands of times more massive than the Sun. These titans lived fast and died young. Fueled by their enormous mass, they burned through hydrogen in only a few million years, a heartbeat compared to the Sun's 10 billion year lifespan. Their brilliance was fierce, flooding the early universe with ultraviolet radiation. That light began to carve through the fog of neutral hydrogen, pushing the cosmic dark ages toward their end. But it was in their deaths that these stars left their most enduring mark. When such colossal stars collapsed, they exploded as supernovae of unimaginable power, scattering the first heavy elements into space: carbon, oxygen, silicon, and iron. The building blocks of planets and life did not exist before these stars forged them in their cores and flung them into the void. Every atom of calcium in our bones, every molecule of oxygen we breathe, every bit of iron in our blood was once created in the heart of a population 3 star. And yet no one has ever seen one. By the time the Milky Way formed, these stars had long since died, their ashes recycled into later generations. What we see today are their descendants. Population 2 and Population 1 stars enriched with metals from countless stellar deaths. To detect the first generation directly is one of Webb's great goals, a task as challenging as it is profound. The clues are indirect but compelling. Ancient galaxies that Webb has already revealed show chemical fingerprints suggesting they were shaped by early supernovae. The absence of metals in certain stellar populations hints at pristine origins. Somewhere in the faintest galaxies at the farthest distances may lie the last survivors or the dying echoes of these first stars. Finding them would not only confirm our theories but rewrite the timeline of cosmic history. If population 3 stars formed earlier more abundantly, or with different properties than we expect, it would reshape our understanding of how quickly the universe moved from simplicity to complexity. For now, they remain ghosts, theoretical giants whose ashes we carry in our bodies but whose faces we have never seen. Webb is our best hope of glimpsing them not as individuals but in the glow of their galaxies, the chemical trails they left behind, and the reionization they helped ignite. To search for population 3 stars is to search for our own beginnings. They were the furnaces that transformed a barren cosmos into one capable of life. Without them, there would be no Earth, no oceans, no breath, no story to tell. The reign of the first stars was brief, but their influence was eternal. Population 3 stars lived into a universe unprepared for them, and in burning so fiercely they transformed everything around them. Their ultraviolet light tore through the fog of neutral hydrogen, creating vast ionized bubbles that grew and overlapped. Slowly, the cosmos shifted from darkness to transparency, a process we now call reionization. As these titans reached the ends of their short lives, they exploded in cataclysmic supernovae. Some collapsed directly into black holes, seeding the centers of young galaxies. Others scattered heavy elements into space, enriching the once pristine gas with the raw materials of complexity. For the first time, the universe contained the chemistry of life. This cycle of birth and death created a feedback loop. Enriched gas cooled more efficiently, allowing new generations of stars to form more steadily. Smaller, longer-lived stars began to appear, the ancestors of those we see shining today. Out of these stellar nurseries, gravity-bound stars together into clusters. Clusters merged into larger structures, and soon the first galaxies were born. These galaxies were not like the majestic spirals and ellipticals we know now. They were small, irregular, fragile cosmic infants. Many flickered out quickly, torn apart by interactions or consumed by their own black holes. But others survived, merging and growing, becoming the scaffolds of larger galaxies to come. From these humble beginnings, the grand architecture of the universe arose. Webb's deep field images have captured glimpses of galaxies so distant that their light has travelled more than 13 billion years. In them, astronomers see the faint outlines of this era. Small compact galaxies glowing with the light of countless young stars. Some appear surprisingly massive, their growth seemingly too fast for the short time since the Big Bang. These discoveries challenge our models, suggesting that population 3 stars and their aftermath may have been more efficient at shaping galaxies than we imagined. In the ashes of the first stars lay the blueprint for everything that followed. The heavy elements they forged seeded future worlds. The black holes they left behind may have grown into the supermassive monsters anchoring galaxies today. Their explosions lit the fuse of cosmic evolution, setting the stage for billions of years of structure complexity and life. To understand the end of population 3 is to understand the beginning of galaxies. One story flows into the other like night giving way to dawn. The first stars died, but in their death they created the conditions for everything else to live. When Webb first turned its gaze deep into the cosmos, astronomers expected to find faint smudges of light, small fragile galaxies struggling to form in the first few 100 million years after the Big Bang. What they did not expect was abundance. Webb revealed galaxies that were brighter, larger, and seemingly older than theory allowed. The early universe, once thought to be a quiet nursery, turned out to be a bustling metropolis. In Webb's deep field images, some galaxies appear just a few 100 million years after the Big Bang, yet already containing billions of stars. According to our models, such rapid assembly should have been impossible. Gas clouds should have taken longer to collapse, stars longer to form, and structures longer to stabilize. Yet there they were, galaxies with mass and brightness rivaling much later epochs. This discovery has forced cosmologists to rethink their assumptions. Perhaps the first stars formed more efficiently than expected, triggering cascades of starbirth that lit up the young universe. Or perhaps our understanding of dark matter and its role in shaping cosmic structures is incomplete. Dark matter halos may have gathered faster, providing the gravitational wells for galaxies to form earlier. Some suggest that Webb is showing us a selection effect, that we're glimpsing only the brightest galaxies, the rare outliers that happen to assemble quickly. But even so, their presence is a puzzle. For every early giant we see, countless smaller galaxies must also exist hidden just beyond Webb's reach. Together they tell us the universe was far busier, far more creative than we had imagined. These early galaxies also reveal diversity. Some are compact and dense, glowing with furious star formation. Others are diffuse, irregular, as if caught in the act of merging. In their light, stretched into the infrared by more than 13 billion years of cosmic expansion, we glimpse the raw beginnings of galactic evolution. Spirals, ellipticals, clusters, all the familiar shapes began here in these chaotic cradles. The implications ripple outward. If galaxies formed earlier, then black holes may have grown faster. If star formation was more intense, then the chemical enrichment of the cosmos may have begun sooner. Every element we find in our bodies today may have its origins closer to the Big Bang than we once thought. Webb has not solved the mystery. It has opened it wider. Each deep field is a challenge to cosmology, a reminder that our models are guides, not guarantees. The universe writes its own history, and sometimes it moves faster than we predict. To look at these ancient galaxies is to see the first cities of the cosmos, glowing islands in a vast sea of darkness. They are not just distant. They are ancestral, the foundations on which everything else was built, and they remind us that even in its infancy, the universe wasted no time in creating grandeur. Among the most startling revelations of Webb's early surveys are signs of massive black holes lurking in galaxies that should have been too young to host them. According to theory, black holes grow slowly, feeding on gas and stars over billions of years. Yet Webb has revealed quasars, galaxies blazing with energy from central black holes, millions, even billions of times the mass of the Sun, existing less than 1 billion years after the Big Bang. How could such monsters have grown so quickly? One possibility is that the first stars, those immense population 3 giants, collapsed directly into massive black holes at the end of their brief lives. Instead of starting small, they began with seeds dozens or even hundreds of times more massive than the Sun. From there, accretion and mergers could have driven rapid growth. Another idea is even more radical, that in the dense, chaotic early universe, entire clouds of gas may have collapsed directly into black holes, skipping the stage of star formation altogether. These direct collapse black holes could have given galaxies a head start, providing gravitational anchors around which matter gathered. Whatever their origins, these early black holes likely shaped their host galaxies in profound ways. As they devoured matter, they released enormous amounts of energy, heating and stirring the surrounding gas. This feedback could both stimulate and suppress star formation, creating a delicate balance that influenced how galaxies grew. In this sense, black holes were not just destroyers but architects sculpting the young cosmos. Webb's sensitivity allows astronomers to study these objects in detail. capturing the faint light of their host galaxies while dissecting the spectra of their brilliant accretion disks. Already it has identified candidates that push the boundaries of theory, black holes with masses difficult to explain given the short time available. Each one deepens the mystery of cosmic dawn. If black holes were indeed present so early, then they may also explain the rapid assembly of galaxies. With their immense gravity, they could have accelerated the gathering of matter-pulling stars and gas into dense cores. Instead of galaxies growing first and then forming black holes, perhaps black holes and galaxies grew together, each feeding the other in a cosmic dance. This challenges the neat timelines once drawn in textbooks. The universe appears to have built its most extreme objects faster than we thought possible. And if that is true, then the path from simplicity to complexity, from hydrogen clouds to galaxies blazing with stars, was shorter, sharper, and more dramatic than we ever imagined. Webb is showing us that black holes were not latecomers. They were present from the very dawn, shaping the galaxies that would one day shape us. In their darkness lies a crucial piece of the light we see today. The birth of the first stars was not just a local event. Their light transformed the universe itself. Before their arrival, the cosmos was filled with neutral hydrogen, a fog that absorbed radiation and left space opaque. With the ignition of the first stellar furnaces that began to change, ultraviolet photons streamed outward, colliding with atoms of hydrogen and stripping away their electrons. Slowly, region by region, the fog lifted. This process, called reionization, was the great turning point of cosmic history. It was the moment when the universe shifted from darkness to transparency, when light could travel freely across vast distances. Without it, galaxies and stars would remain hidden in a cosmic haze. With it, the grand structures of the universe came into view. The mechanics of reionization remain one of astronomy's great mysteries. How many stars were needed to clear the fog? Did galaxies alone drive the process, or did black holes and quasars contribute with their intense radiation? Webb's task is to find out by peering into the transition period and identifying which sources of light dominated. Already Webb has given us tantalizing clues. Its deep field images show galaxies glowing when the universe was less than 1 billion years old. Their starlight powerful enough to carve bubbles in the hydrogen fog. By measuring the spectra of these galaxies, astronomers can see how ionized the surrounding space was, tracing the progress of reionization. Like cartographers, mapping the spread of dawn. The process was not uniform. Some regions cleared early, lit by clusters of bright stars, while others lagged behind, remaining opaque for longer. Imagine a night sky slowly filling with patches of sunrise, expanding until the darkness was gone. That was reionization, a cosmic dawn, not of one star, but of countless stars working together. The implications are profound. Reionization set the conditions for everything that followed. It determined how galaxies could interact, how radiation traveled, and how matter cooled. Understanding it is crucial to understanding why the universe looks the way it does today. Webb's role is unique because it sees in infrared the exact wavelengths into which the light of that epoch has been stretched. Where Hubble could only hint at the edges of reionization, Webb dives directly into it, capturing the moment when the fog burned away. This was the universe's great unveiling. The curtain lifted and the stage of cosmic history was revealed. The silence of the Dark Ages ended, replaced by the chorus of starlight. For the first time, the universe could see itself. How do we study an event that happened more than 13 billion years ago? The key lies in the faintest traces of light stretched and thinned by the expansion of the universe. For astronomers, these fragile photons are the only messengers from the cosmic dawn, and Webb was designed to catch them. One of Webb's greatest strengths is spectroscopy, the ability to split light into its component colours and read the fingerprints of atoms and molecules. When Webb observes a distant galaxy, its spectrum tells us not only what elements are present, but also how much the light has been redshifted, stretched by the expansion of space. The higher the redshift, the earlier in time we are looking. By studying these spectra, astronomers can determine whether the hydrogen between us and those galaxies was neutral or ionized. Neutral hydrogen absorbs light at specific wavelengths, leaving dark gaps in the spectrum. Ionized hydrogen, stripped of its electrons, allows light to pass more freely. By comparing many galaxies at different redshifts, Webb maps the progress of reionization, showing when and how quickly the fog of hydrogen lifted. Already Webb has delivered surprising results. Some galaxies show clear evidence that they lived in ionized bubbles regions of space already cleared by intense starlight. Others seem smothered by neutral gas, their light dimmed and distorted. This patchwork picture suggests that rionization was uneven, spreading like brush fires across the universe rather than a uniform glow. Webb has also detected strong emission lines from elements such as oxygen and neon in some early galaxies. These lines hint at vigorous star formation, the kind of activity needed to drive reionization. The presence of such elements so early also means that the first generations of stars had already lived, died, and enriched their surroundings, speeding up the process of cosmic transformation. Each spectrum Webb captures is a time capsule. Taken together, they form a timeline of the universe's awakening. Within a few years, astronomers hope to pin down not just when reionization began and ended, but exactly which kinds of sources, stars, galaxies, quasars were most responsible. The importance of this work cannot be overstated. Reionization was the last major phase change of the universe the moment it became transparent and structured. Without it, light could not travel, galaxies could not interact, and cosmic history as we know it could not unfold. Through Webb's golden mirrors, we are not only detecting the glow of ancient stars, we are watching the very act of transformation, the moment when darkness yielded to light and the stage was set for everything that followed. As the first stars lit the darkness and galaxies began to take shape, another level of structure emerged. Clusters of galaxies bound together by gravity. These clusters were the universe's first great landmarks, vast beacons marking where matter had gathered most efficiently. To see them at such early times is to glimpse the scaffolding on which the cosmos would eventually be built. Clusters are more than simple gatherings of galaxies. They are ecosystems. Within them, galaxies collide, merge, and exchange material. Their combined gravity bends space itself, magnifying and distorting the light of more distant galaxies in a phenomenon known as gravitational lensing. This lensing not only reveals the hidden distribution of dark matter, but also provides Webb with natural telescopes, boosting its ability to see the faintest objects from even earlier epochs. Webb's deep field images, many taken by staring through massive clusters, have uncovered galaxies that would otherwise be invisible. Some of these lensed galaxies are so far away that their light began its journey when the universe was less than 1 billion years old. Magnified and stretched, they offer rare glimpses of star formation in its infancy. Without the gravitational aid of clusters, even Webb could not detect them. The clusters themselves also tell a story. They are filled with hot gas that glows in X-rays, invisible to Webb but studied by other telescopes. They are dominated by dark matter, revealed only by their gravitational effects. Webb adds a crucial piece by showing how their galaxies evolved, which are young and bursting with stars which are quenched and fading, and how interactions within the cluster drive these transformations. The existence of such massive clusters so early in cosmic history is another surprise. Theory suggests it should take billions of years for gravity to gather so much mass in one place. Yet Webb has revealed clusters forming within the first few billion years, hinting that cosmic structure may have grown faster than expected. In this way, clusters are both tools and mysteries. They act as magnifying glasses, letting us peer deeper into time. They also serve as tests of cosmology, challenging our understanding of how quickly matter can clump and galaxies can grow. Each one is a monument to gravity's relentless pull, and a reminder that the universe has been building grand structures since its earliest days. To see these clusters with Webb is to see the pillars of the young cosmos. They stand as milestones between the first stars and the vast cosmic web that spans the universe today. Through them, we trace the path from the small and simple to the vast and complex, a path that ultimately led to galaxies like our own. In the beginning, the universe knew only simplicity. Hydrogen and helium filled the cosmos, born in the first minutes after the Big Bang. These elements were abundant, but they alone could not build worlds or life. For that, heavier elements were needed: carbon, oxygen, nitrogen, iron, silicon. And those would come not from the Big Bang itself, but from the furnaces of stars. The first generation of stars, those immense population 3 titans, were the forges. In their blazing cores, hydrogen fused into helium and helium into heavier nuclei. But their true gift came in death. When they collapsed and exploded as supernovae, they scattered newly minted elements into space. For the first time, the universe was seeded with the raw ingredients of complexity. This cosmic alchemy set the stage for everything that followed. Clouds enriched by heavy elements cooled more efficiently, forming new stars more quickly. Dust grains condensed, clumping into the building blocks of planets. Oceans, atmospheres, and even the chemistry of life all depend on these elements forged in stellar fire. Without those first explosions, Earth could never have existed, and neither could we. Webb's instruments allow us to trace this enrichment in the earliest galaxies. By capturing the faint glow of oxygen or neon emission lines, astronomers can measure how quickly the universe became chemically diverse. The surprise is how early these signatures appear. In galaxies less than 1 billion years old, Webb has already found evidence of oxygen, proof that entire generations of stars had lived and died in astonishingly short time frames. This rapid chemical evolution challenges our sense of pace. We once imagined a slow, gradual build-up, but Webb shows us a universe in a hurry. Heavy elements were forged and spread with startling efficiency, making the cosmos ready for planets, and eventually for life far sooner than expected. And yet mysteries remain. Some early galaxies seem richer in metals than theory predicts, while others remain pristine, almost untouched. This patchwork suggests that enrichment was uneven, driven by local bursts of star formation and violent feedback from supernovae and black holes. The early universe was not uniform in its chemistry. It was a mosaic, with some regions racing toward complexity while others lingered in simplicity. For us, the significance is deeply personal. Every breath we take carries oxygen once born in the core of a long-dead star. Every cell in our body contains carbon and nitrogen created billions of years before Earth formed. To study the birth of heavy elements is to study our own ancestry at the most fundamental level. Through Webb, we are not only watching galaxies assemble, we are witnessing the universe learning to write in a richer alphabet, expanding from hydrogen and helium to the full vocabulary of matter. In that vocabulary lies the story of planets, oceans, and life itself. The first stars were spectacular, but they were also unstable. Their enormous masses made them short-lived, burning out in only a few million years. They lit the cosmos and forged the first heavy elements, but they could not last. For the universe to mature, it needed something different. Stars that would burn more slowly, shine more steadily, and create environments where planets and life could one day take hold. This transition from titans to long-lived stars was a pivotal moment in cosmic history. As the ashes of population 3 stars enriched the gas around them, the chemistry of star formation changed. Cooling became more efficient, allowing smaller stars to form. These were still luminous, but many had lifespans measured not in millions, but in billions of years. Some of them still shine today, ancient red dwarfs that have endured since the dawn of galaxies. Among these new generations were stars like our Sun, stable middle size and long-lived enough to nurture planetary systems. For the first time, the universe could create not only brilliance but stability. Planets orbiting such stars had the time to form, evolve, and potentially support life. The cosmic stage was no longer a place of brief, violent bursts. It became a place where patience and endurance mattered. Webb's observations allow us to study this transition in real time, not in our backyard, but across billions of light years. By analysing the spectra of early galaxies, astronomers can measure the ratio of massive short-lived stars to smaller, longer-lived ones. The data show that the balance shifted surprisingly early. Within the first billion years, the cosmos was already producing stars that could endure for ages, laying the groundwork for planetary systems and biological potential. This shift had profound consequences. Long-lived stars not only stabilized galaxies, they also created steady radiation fields that allowed atmospheres to persist. They produced heavy elements more slowly but more consistently, spreading them through interstellar space. And with their gentler winds and supernovae, they allowed delicate structures like protoplanetary disks to survive. Without this transition, the universe would have remained a place of fleeting brilliance and constant upheaval. Instead, it became a place where continuity was possible, where stars could shine for eons and where evolution, cosmic and biological, had the time to work. In a sense, these later stars are less dramatic than their colossal ancestors, but they are far more important. They are the architects of galaxies, the anchors of solar systems, the quiet engines of cosmic history. They are the reason life had the time it needed to emerge on Earth and perhaps on countless other worlds. Through Webb, we can see the dawn not only of light but of longevity, the moment when the universe learned to trade spectacle for stability, and in doing so prepared the way for life. Once long-lived stars began to appear, the universe entered a new era. Around many of these stars, the leftover gas and dust did not simply disperse. Instead, gravity and motion caused it to flatten into swirling disks, cosmic workshops where planets could be built. These protoplanetary disks were the cradles of future worlds, the places where dust grains collided, stuck together and grew into pebbles, rocks, and eventually planets. The ingredients were richer now. Thanks to the first generations of stars, the gas contained more than hydrogen and helium. It carried carbon, oxygen, silicon and iron, the raw materials of rocky worlds and complex chemistry. Within these disks, ice formed in the colder regions, while metals and minerals condensed closer to the parent star. The architecture of entire planetary systems was sketched in these spirals of dust. For astronomers, these disks are keys to understanding how common planets might be and what kinds of planets can form. Earlier telescopes like Hubble and ALMA gave us glimpses of such disks, often showing striking rings and gaps where young planets were already carving paths. But Webb has taken this to a new level. Its infrared vision can pierce through dense clouds of dust, revealing the hidden chemistry of these nurseries. Already, Webb has detected water vapor, carbon dioxide, and organic molecules in disks surrounding young stars. These are not abstract signatures, they are the essential components of atmospheres, oceans, and potentially biology. To see them present so early in the life of a star system suggests that the building blocks of habitability appear almost as soon as stars themselves. The structure of the disks is equally revealing. Some show sharp divisions, evidence that giant planets are shaping them. Others appear turbulent with gas streaming inward and outward. Each disk is a snapshot of planetary formation in progress. Frozen at stage, our own solar system passed through more than 4 billion years ago. The implications stretch far beyond curiosity. If protoplanetary disks routinely contain water and organic compounds, then the seeds of life may be sown across the galaxy. Planets may form not in sterile emptiness, but in environments already enriched with chemistry that leans toward biology. Webb's role in this story is crucial. By studying disks at different ages, it creates a timeline of planet formation, from newborn stars wrapped in thick cocoons to mature systems where planets have cleared their paths. In doing so, it helps answer one of the deepest questions. Is the emergence of habitable worlds a rare accident or a natural consequence of cosmic evolution? To look into these disks is to look into the past of Earth itself. Once our solar system was just such a whirl of gas and dust carrying the same elements and the same potential. Out of that chaos came oceans, continents, and life. With Webb, we see that we are not unique. The universe is filled with such beginnings. The earliest galaxies were small and fragile glowing islands of stars adrift in the cosmic sea. Yet from these modest beginnings arose the immense spirals and ellipticals we see today. The process that bridged this gap was not gentle. It was violent, chaotic, and creative. The merging of galaxies. In the young universe, gravity pulled small galaxies together. Collisions were inevitable. When two galaxies met, their stars often passed by each other unharmed, but their gas clouds crashed and compressed, igniting furious bursts of star formation. Black holes at their centers feasted, growing larger with every merger. Step by step, small fragments coalesced into larger structures. This hierarchical assembly is one of the central pillars of modern cosmology, but until Webb, direct evidence of it in the early universe was scarce. Hubble showed us galaxies at intermediate ages, some caught mid-collision, but the faintest and earliest stages remained hidden. Webb's infrared vision has changed that. Its deep images reveal galaxies caught in the act of merging when the universe was less than 1 billion years old. Some of these mergers are spectacular. Webb has captured distorted shapes, galaxies stretched into arcs and tails by tidal forces, their stars scattered into faint streams. Others show compact knots of intense star formation, where gas has been squeezed into stellar nurseries. These are not accidents, but the engines of growth, the way the cosmos built its grandest cities. The discovery that such mergers were common so early challenges our timelines once again. Galaxies did not wait billions of years to assemble. They were colliding and combining from the start, creating structures far larger and more complex than we predicted. This rapid growth may help explain why Webb sees massive galaxies so soon after the Big Bang. The story of our own Milky Way is written in this history. Our galaxy likely grew from dozens, perhaps hundreds of smaller ones. Its stars carry the chemical fingerprints of these ancestors, each merger, leaving a mark in the distribution of elements and stellar orbits. By studying early mergers with Webb, astronomers are reconstructing not only cosmic history, but our personal galactic genealogy. There is beauty in this violence. From the chaos of collisions came stability. From shattered fragments came order. Every majestic spiral, every giant elliptical, every cluster of galaxies began as a swarm of tiny sparks drawn together. Webb shows us the process in action, reminding us that destruction and creation are often two sides of the same cosmic coin. To see these merging galaxies is to witness the universe building itself. The small became great, the simple became complex, and in their light we see the blueprint of our own home written across the vastness of time. The universe is not random. Though galaxies seem scattered across the night sky, they are woven into a grand design, the cosmic web. Vast filaments of dark matter and gas stretch for hundreds of millions of light years, connecting clusters of galaxies like beads on a string. Between these filaments lie enormous voids, regions almost empty of matter. Together they form the largest structure in existence, a cosmic skeleton on which the universe is built. This web began to take shape during the cosmic dawn. As matter fell into the invisible scaffolding of dark matter, gas streamed along filaments, feeding the growth of galaxies and clusters. The first stars and galaxies were not isolated. They were nodes in this emerging network. To understand how the universe evolved, we must see not only galaxies themselves, but also the threads that bind them. Until recently, these filaments were nearly impossible to observe directly. Their gas is diffuse and faint, glowing only in the dim light of hydrogen. But Webb's extraordinary sensitivity in the infrared has begun to change that. By capturing the faint signatures of distant galaxies aligned along filaments, Webb offers indirect glimpses of the web in its infancy. Patterns of clustering shapes of protoclusters and alignments of galaxies hint at the strands of structure stretching across space. Some of Webb's deep field images already suggest the presence of elongated groups of galaxies, the embryonic filaments of the cosmic web. These alignments are not accidents. They are the fingerprints of gravity guiding matter into highways that would later grow into colossal structures. By mapping them, astronomers can compare reality with simulations testing our understanding of dark matter and cosmic evolution. The cosmic web is more than scaffolding. It is a circulatory system channeling gas into galaxies and fueling star formation. Without these flows, galaxies would starve, their light fading. With them, galaxies flourish, growing brighter and richer in stars. To study the web is to study the lifelines of the cosmos itself. For us, the implications are staggering. Our own Milky Way resides in one of these filaments, part of a vast structure known as the Laniakea supercluster. The stars above us, the atoms within us, all trace their origins to this interconnected network. Webb, by revealing the faint outlines of the web's first threads, is showing us the blueprint of our cosmic home. In the delicate glow of galaxies stretched across billions of light years, we glimpse the hidden architecture of creation. The cosmic web is the bridge between the chaos of the Big Bang and the order of the modern universe, a bridge that Webb is finally allowing us to see. To peer into the cosmic dawn is not just to study the past, it is to confront the question of origins not only of galaxies and stars, but of ourselves. Every atom of calcium in our bones, every drop of oxygen in our lungs, every spark of iron in our blood was forged in the fiery deaths of ancient stars. When Webb captures the faint light of those first galaxies, it is revealing the very furnaces that made us possible. This knowledge changes perspective. For centuries, humanity saw itself as separate from the heavens, gazing upward at stars as distant, untouchable lights. Now we know they are kin. Their chemistry flows through us. Their history is our history. By watching the universe awaken, we are watching our own beginning written across time and space. The emotional weight of this realization is profound. To see galaxies forming when the universe was only a few 100 million years old is to see the first brush strokes of a cosmic masterpiece. It is to realize that creation was not a singular moment, but an unfolding process, one that continues even now. Galaxies still collide and merge. Stars are still born and die. The story that began in the cosmic dawn continues in every sunrise here on Earth. Webb has made this story visible. Its golden mirrors gather photons that left their sources before our planet existed, before the Earth itself had coalesced from dust. That light travelled across billions of years to meet us now, a silent message from the dawn. We are the first generation capable of reading it, of turning ancient radiation into knowledge and meaning. And in doing so, we're reminded of our fragility. Against the scale of billions of light years, our lives are brief. Against the scale of cosmic time, our civilizations are young. Yet the fact that we can look back so far that we can reconstruct events at the edge of time is itself extraordinary. It means that the universe has grown not only galaxies and stars, but minds capable of wondering where they came from. The cosmic dawn is not only an era in history, it is a mirror. It reflects the possibility that intelligence was always seeded in the stars, waiting for matter to arrange itself into beings who could ask questions. When Webb shows us the first galaxies, it shows us not something foreign, but something deeply familiar. It shows us home at the scale of the universe. The universe began in darkness, a silent expanse of hydrogen and helium, adrift in endless night. From that stillness came the first spark stars that blazed galaxies that grew light that spread. Webb has given us a way to witness this transformation, to see the moment when the cosmos awoke. In those ancient furnaces, the raw materials of life were forged. In those first galaxies, the blueprint of the modern universe was drawn. Every planet, every ocean, every living creature traces its ancestry back to that dawn. To study it is not to look at something far away, it is to look at the roots of who we are. This is why the cosmic dawn matters. It is not only a scientific milestone, but a human story. It tells us that creation is not finished, that the universe is still unfolding, still building, still alive. And it invites us to see ourselves as part of that story, brief in years but eternal in origin. So as Webb continues its silent watch-gathering light that has travelled across 13 billion years, we are left with a question. If the cosmos has already given rise to us, what else might it hold? What other dawns, what other stories are waiting in the dark? The search continues. The light is still arriving, and the universe still has secrets to share. Thank you for joining me on this journey into the first chapter of time. The next chapters are waiting, and together we will keep reading the stars.